Good day, my dear warriors. Welcome to the Vedantu English channel, and this is your capto. Yes, good day. I'm very good. Thank you so much. Welcome. I hope I'm audible and visible to all of you. Yes, yeah. Today we are taking up the next detailed topic right from the basics, and then we will see the concepts. We'll see all the diagrams. We'll apply these concepts in the solved examples. We'll also go to the PYQ level, everything in today's lecture, right? So it's a one-shot class and such a beautiful image. Which other chapter? Yeah, all the warrior pandus, WP. Yeah, trending in the chat box. Thank you. Yes, it is the chapter of your gravitation and complete gravitation chapter. Now this gravitation chapter includes your Newton's laws, then the potential energy formula, then the gravitational acceleration below the surface, above the surface, at the surface. Then we have the satellite theory, okay, and the energy of satellite related things. There are some extra things like field, potential, Kepler's, sometimes they are also deleted, sometimes they are also included. We will try to cover that also. Although the concept of field and potential, if you remember, is also there in electrostatics, but we will try to, do those things also over here only. All right, so that is the target of today's lecture. Yes, I am having a great day. Good day to all of you. Thank you so much. Yes, thank you for lighting up the chat box as well. Thank you guys. Means a lot, all the warrior pandus. Those of you who do not know me, my name is 𝐂𝐡𝐞𝐤 Shreyas. Yes, I have been teaching physics for more than 13 years, sending kids to the top-notch colleges. And now this year it is your turn. Remember that. Okay? So make sure you are subscribed onto the channel. Yes, the #1 English channel in the country. And make sure that you are also liking this particular video. Do not let YouTube think that you are not interested in NEET. When you like, YouTube understands that, okay, this kid, this student is interested in, whatever, the exams, right? So make sure you are subscribed to the channel. And remember, the scholarship test has already begun. Just yesterday, on Sunday, thousands of students across so many centers gave MVSAT. Now, the last offline MVSAT will happen on 27th of October, and online is still going on. If you have missed any of the offline dates, then make sure you are at least going on 27th, and also the online registrations should continue. Make sure that you are not only registering but also giving the test, because only when you give the test you will get important questions for your exams. You will get test series, mock test papers, counseling session is there. Also you have those of you who perform little bit better, you get digital access to some books and libraries. You also get some mind maps, revision notes, practice tests. All these things are a part, and if you do exceptionally well, then you can get scholarships also. And if you do even better, you can even win even better prizes, like winning a trip to some Universal Studios, PlayStations, iPads, so much more. So also you will get to know where you stand at a national level, because thousands of students, I don't know how many of you have seen those videos, thousands of students, check out our Instagram page, have given the test just yesterday. And if you have given the test already, very good. Do let me know. Okay, like the video, smash the like button, subscribe to the channel. Let's begin then. Hello. Yes, your turn will be this year. Great. All right. Now, when we talk about Newton's law of gravitation, so Newton, back in the 1700s, he thought of one simple thing. He saw that if there is an apple from the tree and if it is falling, and he saw that it was not just falling but also accelerated. It was also accelerated. So he thought, according to his own law, if something has acceleration, if something has mass, then that thing must also experience a force. So by Newton's law, there must be a force acting on that apple because of which it is accelerated. Because the acceleration was down, he concluded that the force was there downwards. This was a mysterious force for him. He then thought, not just apple, anything, even a stone, even one rock, even a person is getting pulled towards the earth, and all of them, experience that force in such a way that the force was directed towards the center of the earth. Wherever you go, if you are standing here, if you are standing here, if you are standing here, every time the force was directed towards the center. He thought I should do more research, and then he understood that, okay, even if I take the moon, actually even the moon is falling onto the earth. You'll be like, sir, what are you saying? How can moon fall onto the earth? See, just imagine something. You are on a cliff and you throw something. Let's say it falls over here. Imagine you throw it with slightly higher speed, it falls over here. It is still falling onto the earth, right? It is falling onto the earth. You are standing on a hill. You throw it with more speed, it will fall over here. You throw it with even more speed, trust me, it will probably hit you from behind. You'll be like, sir, I threw it front. How did it come from behind? The reason for that is earth is round. And you were standing on a hill somewhere here. First time it fell here, second time it fell here, third time it fell here, fourth time with large speed it was trying to fall, but even the earth was bent. Even the earth is curved. So as it falls, the earth's curvature is falling or turning by the same amount. So the stone feels or gets fooled into thinking that, okay, I will reach the surface of the earth someday, but it never reaches because that cat and mouse game will continue. That chase will continue. The stone will try to fall, the earth is curved. The stone will try to fall, the earth is curved, and you will complete a circular motion. So even that stone going round and round the earth is a free fall. So Newton thought, imagine 300 years back, that actually the moon is falling onto the surface of the earth. It's just that it's like a cat and mouse game, but it will never actually touch the surface of the earth. It will just keep doing circular motion. So even this is going to do free fall motion. And then he was able to also see that, okay, even this guy has some kind of acceleration and there must be a centripetal force using the knowledge of circular motion. And he again saw F is equal to mass of the moon into acceleration of the moon. So from this he was able to conclude that earth not only attracts apples, stones, people, but even the moon. Then he thought maybe even the sun attracts the earth, and he was able to finally conclude that any masses anywhere in the universe always end up applying a force on each other. And this mysterious force back then, he then labeled it as gravity or gravitation. I hope this is clear. Yeah, the session will be around 3 hours, you can say. So this is how he was able to see that any objects with any kind of mass attract by a force towards each other, and this is a universal law, attract each other, okay, which is called as gravitational force, which is basically called as your gravitational force. Then he conducted more experiments, and then he was able to finally figure out his actual law. So let's have a look at that particular law, guys, right now. So what is his actual law that he found out? He finally concluded that if you have two masses or three masses, we'll come to that also. If you have two masses and then you draw a line joining those two masses, those particular two masses, let's say the separation between them is r, then both these masses end up attracting each other. You cannot say m1 is more, so force will be more on m1, or m1 will apply more force on m2. No, both these forces will be equal and opposite. Why? Can you think and put it in the chat box? Yeah. Yes. So all those details regarding pattern, everything, don't worry. I'll make a separate video when anything comes up. Don't worry. Yeah, concentrate on the class. Any other doubt, please put it up in the comments after the class. Let's not break the flow. Yeah, these two forces will be always equal and opposite. Yes, they will be equal and opposite because of Newton's third law. Correct. So, I will call as R being the separation between the masses. Separation between those masses. Next important thing, F is the gravitational attraction. It basically follows the third Newton's law of motion. Basically, you can see the action. If this is action, this is reaction. If that is action, this is reaction. Action-reaction rule. And it is always attractive. It is always attractive. It is not like it will sometimes repel. See, in electrostatics, charges are of the same sign, the force is repulsive. If they are of opposite sign, it is attractive. But in gravity, it is not like that. It is always attractive along the line joining the forces. Along the line joining the masses, along the line joining the masses. Very, very important. It will never be like the masses are like this. One is here, the force is here at some angle. No. Or the force is like this. No. Remember, in magnetism, the charge is moving somewhere, field is somewhere, the force is only somewhere. QV cross B. That was in magnetism. But in gravity, always wherever the two masses are, direct line of sight, you will see the forces will be along those line joining those two masses. Okay, I hope this is absolutely clear. Yes. Regarding the crash course, I will tell you in a separate video, don't worry. Yeah. Okay. Now, as per this particular law, the force was found to be proportional to the product of the masses, that means M1 and M2. Also, this particular force was found to be inversely proportional to the square of the distance between them. That is why it is also called as the inverse square law, inversed square law. That is the law name which is given because it is inversely proportional to the square of the distance between them. Therefore, our force of gravity is nothing but, there is a constant, we will call it G, M1, M2, which is the product of the masses, and the whole thing is divided by the square of the distance between them. So this is our gravitational force value. Direction wise, we know it is always going to be attractive along the line joining the masses. This particular G is called as the universal. It is not acceleration due to gravity, it is universal. Small g is gravitational acceleration on Earth, which is 9.8. On Moon it is something else, on Jupiter it is something else. So it is not universal. This capital G is this law's constant. So this is the universal constant, universal gravitational constant, universal gravitational constant. Can you quickly recollect and tell me what was the value of that? Yes, we'll come to that, whether it's a weak force, strong force, everything, I'll come to that. Yes, what is the value? 6.67 10 to the power minus 11. Unit wise, you can see, take r square on the top, which is meter square. This is Newton. Kg is kg square. Kg square comes below. So Newton meter square per kg square. That will be the value. Unit. This will be the value. Is that right, everyone? Okay. Another important thing which you should definitely know about gravitation. Don't worry, all these notes you will be getting it in the PDF after the session is over. Make sure you are joining the official Vedantu English group. You will be definitely getting it. Okay. Another important thing which you should know. Imagine if some villain comes in between and stands in between. some mass. He's like, you can't see the mass. Does not mean their love will go away. Their love will still be there. They will still attract each other. Imagine this M1 is like Pandu, this is like Champa. If some villain comes and stands in between, just because Pandu can't see Champa, doesn't mean he will not attract Champa. Champa still loves Pandu. Pandu still loves Champa. So they will still attract each other. So even if some mass comes in between, their force will not go away. So I'll mention that as well. The presence of any other mass doesn't affect their mutual gravity. It won't be affected. Keep that in mind. Another important thing, it is a very weak, in fact, it is the weakest force in nature, but it is the longest range force. There are 4 forces in nature, fundamental. Everything else is different, you can say derivations or modifications of these forces. The 4 fundamental forces are gravity, electromagnetic, weak nuclear, strong nuclear. Electric and magnetic are combined together by Maxwell and Faraday and all those people. So they are actually one and the same thing, electromagnetic. So we have gravity, electromagnetic, weak nuclear, strong nuclear. Out of that, strong nuclear is the strongest force in nature, then weak nuclear, then electromagnetic, and then the weakest of them all is gravitational force. Range-wise, the strong nuclear force is very, very short range. Then the range is slightly better for weak nuclear, even better for electromagnetic, and it is the largest or the longest range for gravitational force. Is this absolutely clear, everyone? Understood? Some of you had that doubt, so hopefully that is absolutely clear. Yes. Now this particular law is in the scalar form. Sometimes in the boards and some weird examinations, they will ask you the vector form. No issues. Say for example, we want to write it in the vector form and we want to see what that formula will be. So say for example, with respect to mass 1, I am looking at mass number 2. This is the position vector. So R is basically written down as R21. So R21, which is R2 minus R1, is the relative position of mass number 2 with respect to mass number 1. Of mass number 2 with respect to mass number 1, that is R21. R21 is R2 minus R1. V21 is V2 minus V1. A21 is A2 minus A1. Where did I get this from? Relative motion chapter. Anything 21 will be that vector minus that second symbol will come later on. If it was R12, it will be R1 minus R2. So this is how it works. So then you can see the force which is acting on 2 because of 1. So what is F21 then? F21 is basically the force on 2 because of 1 will be in the vector form given by the magnitude multiplied by the unit vector along that direction. Anything, when I say 5 I cap, 5 is the magnitude. I cap does not have magnitude. In fact, the magnitude is 1, unity. So direction is given by that I cap. So same way, any vector can be represented as the magnitude into the unit vector. We have seen that in the chapter of vectors. So what is the magnitude of this particular F21? Well, magnitude we have already seen over here. So let's just put that as it is. So it is G, product of the masses, M1, M2, the whole thing divided by the distance. Distance is R21, square it. What about the unit vector? if you notice, R21 is here, F21 is opposite. So think about it, there will be a unit vector. There will be a unit vector called R21 cap. R21 cap. It's exactly opposite. The force vector is exactly opposite of the unit vector of the position. So can I put minus R21 cap? That's it. That is the answer. So if you want, you take the minus sign over here. Okay, minus sign over here. You have your R21 square over here. You have R21 cap over here. That's it. So this is basically your F21 G into M1 M2 over here. So this is the vector formula. This is what? This is the vector formula. This is nothing but your vector formula of gravitation. Usually you do not use this. Usually we use this only because it is very simple. There is no complications of this relative vector, negative sign and all of that. That's all. Did you understand why the negative sign came? Because direction wise this force is opposite in direction to the yellow, the position vector. That's why the negative sign came. Otherwise you don't need. This vector form you have also seen in electrostatics. It's also there in electrostatics. Correct. Next important thing, guys. Imagine there is a mass m1 here, there is a mass m2 here, there is m3, m4, m5, m6, like that mnth mass is there here, and there is one more mass over here. Let's just call it as m. Then what will happen is, you can see this mass is at some distance from m1, some distance from m2, some distance from m3, m4, m5, like that, mn. And these are the distances. Let's say I call it r1, r2, r3, r4, like that, rn. Each of these masses will pull this mass by some force. Will pull this mass by some particular force. Maybe the forces are like F1, F2, F3, Fn. So F1, F2, like that, Fn are the mutual forces of gravity, mutual gravitational forces. So what will be the net force on, that mass m is given by superpositioning, is given by the superpositioning of all the mutual gravitational forces. That is by vector addition. By vector addition. So whatever is that total force, my dear students, it will be just F1 bar plus F2 bar, like that, till Fn bar. So that is given by superpositioning principle. This force will be there, this will be there, this will be there. You do the vector addition, the net force will be just the vector addition of all these forces together. As simple as that. Is that okay, everyone? So superpositioning was also there in electrostatics. It is even there right now over here in gravitation. It was also there in magnetism, everywhere. So superpositioning is definitely valid. Superpositioning. Okay? Cool. Now that we have understood how gravitational forces are, what is the formula, what is their vector form, everything about it, let's start doing some questions now. Let's start doing some questions. Okay, get ready for it. Two masses attract due to gravity by a force of F. If one of the mass is doubled, the other tripled, and their distance of separation is halved. The distance of separation is halved. Then the new force is how much? That is the question. Let's try to solve this. Let's understand it first. Let's assume some two masses. Let's say this is M1, this is M2. There is some separation between them R, and the original force between them is F. Now what you have done, the distance between them is halved. So now those same masses are probably at half the distance. So basically it is R by 2. One of the masses is doubled, so 2m1. The other mass is tripled, so 3m2. So question is, what is the new force between them? So I can call it as F1 or F2 or F prime or whatever you want to call. So what is the new force between them? Is that right? Okay. So if you try to find the new force between them, it will be gravitational constant, the product of the masses, which is 2 times of m1, 3 times of m2, upon the square of the distance between them, which means r by 2 whole square. Let's just rearrange and see what do we get. G into 2 3s are 6, 6 times m1 m2 is there, r square is there, 1 by 2 square is 1 by 4, but that 4 will go on the top. So this will become 24 G m1 m2 divided by r square. Correct? This by 2 square will become 1 by 4, but that 4 will go on the top. 2 3s are 6, 6 into 4 is 24. What is this G m1 m2 by r square? G m1 m2 by r square, that is nothing but the old force. That is nothing but our old force. So hence our new force is 24 times the older force. Very good. Some of you got it. Awesomeness. 24 times of the older force. Great. Great. Very good. Awesomeness. Great. Awesome. Now, next question. This is going to involve 3 masses, and let's see if you can figure this out. Okay, this is going to involve 3 masses. In this situation, imagine you have been given like a triangular thing, and there are 3 masses. Let's say one is m, the other is 2m, and here you have 3m. The question is, find, assuming the side length to be a, find the net force on 3m. Find the net force on the 3m mass. That is the question. Let's try to do this. If you have to find the force on 3m, we'll think who and all will apply the force. M will apply the force, 2m will also apply the force. Okay. So let's go to the solutioning part. On 3m, we'll have 2 forces. One will be because of m, it will be like this. The other will be because of 2m, and it will be this way. Always the forces are attractive. So 3m gets pulled towards 2m, 3m also gets pulled towards m. Both these forces together will produce a resultant force. So obviously we have to use superpositioning theorem, because one mass is being pulled by multiple masses over here. No issues. We'll try to find that. It's not a big deal. So this I will call it F1. This let me call it as F2. Can we quickly think what is the magnitude of F1 and F2? What is the magnitude of F1 as well as F2? I think we can. F1 will be, think about it, G, product of the masses, m into 3m, divided by the distance, which is basically a square. Okay. So this is nothing but 3g m square divided by a square. What is force number 2 going to be? G, product of the masses 2m into 3m, whole thing divided by the distance, which is a square. So 2 3s are 6, so 6. So this is 6 g m square divided by a square. Okay, g m square by a square is common. This is 3, this is 6. That is the only difference that I can see. Okay, now what about the resultant force? What about the resultant force? That is very, very important. This is your resultant force. We can clearly see that F by superpositioning is nothing but F1 bar plus F2 bar. This is using superposition principle. But I'm not interested like that. I'm interested in the magnitude right now. So what is the magnitude of F? Use the vector addition formula. A vector plus B vector's magnitude is A square plus B square plus 2AB cos theta plus 2AB cos theta. Oh, okay. So it will be F1 square plus F2 square plus 2 F1 F2 cos theta. You will be like, what is theta, sir? This is theta. How much will that be, sir? This is equilateral triangle. So can you guess how much this angle should be? Obviously, it should be 60 degrees. 60 degrees. So it will be cos of 60 degrees. Perfect. Okay. Now let's see what is the answer. F1, F2, both have gm square by a square. Both have gm square by a square. So put that gm square by a square term outside. Inside, F1 will have that number 3. So put that number 3 square. F2 will have that number 6, so put that number 6 square plus 2 times of F1 had that number 3, other things have already gone outside, so don't worry about it. 2 into 3, F2 had that number 6 and cos 60 is nothing but half. Is this clear? Is this absolutely clear? Why we took this number outside? Because both of them had gm square by a square common. Everywhere it will come out common. I can take it outside the root as it is. Okay. So what is the next step? G m square by a square. 3 square is 9. 6 square 36. 2 cancel. 6 3s are 18. Okay. What do we get over here? 9 plus 36 is 45. 45 plus 18 is nothing but 63. So root of 63, that's what I will get. Is that right? Everybody with me? Yeah, not 60. Just check everyone again. Yep. Yes. 63. Correct. So g m square by a square root of 63. That is the net force. That is the answer. This is the net force acting on the 3m mass. Clearo, understood? Shall we go ahead to the next part? Shall we go ahead to the next question? Let me know. Clear? Very good. Awesome. Next question coming up on your screen. Here it is. A mass is broken into 2 pieces and separated. So, one piece here, maybe the other piece over here. The mutual gravity will be maximum if the ratio of masses, ratio of the broken masses is question mark. Read the question again, you will understand what is asked. You have a mass, you break it into 2 parts, like you take a stone, throw it on some wall, it breaks into fragments. maybe you have broken into 2 fragments and now you keep them away. You have like 2 rocks, 2 asteroids, 2 planets derived from the same mass. Now you want the mutual force of gravity to be maximum. So what should be the ratio of the masses? That is the question. Okay. So how do we do this particular question? First of all, let's assume that the original mass was m, the new masses are, let's say, m1 and m2. If the new masses are m1 and m2, there will be some gravitational force between them like this. There will be some gravitational force between them like this, which will be given by g m1 m2 divided by r square. As per the question, the mutual gravity should be maximum. That means what I want to do is make this force maximum. I want to make this force maximum. Can I change it? G? No. It's a gravitational constant, universal. I can't do anything. Can I change R? No. They are separated by some distance, so I can't touch R. Can I touch mass 1, mass 2? Yes. The only thing which I can touch is basically these masses. So I want them to be maximum. I want them to be basically maximum. But wait a minute. They were derived from the original mass m. So technically speaking, m is m1 plus m2. But what do I want? But I want m1 into m2, the product, to be maximum. I don't know how many of you know this. This is always going to be true when the masses are equal. There is a property in mathematics. When the sum of 2 numbers is constant, I'll repeat, when the sum of 2 numbers is constant, this m is a constant, their product is maximum when the numbers are equal. Let's give it a try. Let's just take some random value. Let's say our mass was 10 kg. Let's say I break it into 1 kg and 9 kg. Mass is 10 kg. So let's say 2 kg and 8 kg. Let's say mass is 10 kg, then 3 and 7. Mass is 10. Let's break it 4 and 6. Mass is 10. Let's break it as 5 and 5. After this, it will be repeat. It will become 6, 4, 7, 3, 8, 2, 9, 1. It is going to be repeat. What will be their product? 9 ones are 9. 8 twos are 16. 7 threes are 21. 6 fours are 24. 5 fives are 25. After this, again you will get 24. Again you will get 24. Again it will reduce. So can you see this number is obviously maximum, and this is happening when the numbers are equal. Yes, when the numbers are basically equal. Yes, their product is maximum. So that means m1 is to m2. Therefore, the masses should be equal. m1 should be equal to m2. Therefore, m1 is to m2 is nothing but 1 is to 1. 1 is to 1. So what is that important property that we learnt over here? When the sum of 2 numbers is a constant, their product is maximum when the numbers are equal. This is always true. You can use it even in electrostatics, magnetism, anywhere you can use this. Very, very important property, guys. Okay? Very, very important property. When the sum of 2 numbers is same, because you are breaking the same mass into 2 parts, obviously their original mass will be same. Their product will be maximum when the 2 numbers are equal. Okay, so this kind of questions can also come in the examination. All right, let's go to another question, guys, coming up on your screen. This is also very common. They will tell you there are 2 masses, m and 2m. They are separated by a distance of r, and this dual mass system revolves around each other due to mutual gravity. Due to mutual gravity. Find their speeds and time period of revolution. Find their speeds as well as their time period of revolution. Very interesting question, guys. Read the question again if you want to. These two masses are revolving around each other due to their mutual gravity. Question is, find their time period as well as their speeds. First of all, let's understand why are they revolving around each other. Only then we can think ahead. See, I'll tell you what in this particular question. Let's go step by step. There will be a force like this. There will be also a force like this. These forces will be equal. We know that. If you ask me what the value of the force is, I will quickly tell it is G m 2m divided by r square. This is by Newton's law of gravitation. Newton's law of gravitation. Okay. Next important thing. Whom will they go around? What will they go around? Will m go around 2m? Will 2m go around m? Or will they go around something else? Let's understand that for this particular system, if you consider this as our system, this force technically is internal force. F is, what is F? F is basically internal force for that m plus 2m system. For that m plus 2m system. That means external force is absent. So therefore, center of mass is at rest. It will stay as it is. It will basically stay as it is. Oh, it is going to stay as it is means our center of mass which is there, maybe it is somewhere over here, it will not move. Rather, these masses will go around the center of mass. Therefore, the masses revolve around the center of mass, Yes. So 2m will go around center of mass, m will go around the center of mass like this. Always they will be diametrically opposite. Like this they will go around the center of mass. In their circular orbits. So now it has been converted into a problem of center of mass and circular motion. Center of mass and circular motion. And what did I tell you? Center of mass is a silent killer chapter. Suddenly, zoom, it will come and it will be like, oh, I am there. So center of mass suddenly came into the picture. Okay. Now, will their orbits be of the same radius? Obviously not, because the masses are not equal. Center of mass is closer to 2m and it is far away from m. So m will go on a larger orbit, 2m will go in a smaller circular orbit, because this radius, this distance is smaller. So it will go in a smaller circle. This m will go in a slightly larger circle. So what I will do is, better to draw two circles. This is our center of mass. Our one of the masses, let's say 2m is here. So m will be here. M, if it goes with a velocity of v, 2m will go with a different velocity. That also will come to that in a bit. This will have slightly different velocity. Okay. This, as you can see, is the distance of 2m from the center. This, as you can see, is the distance from the center of mass m. They both are different. Now these are the orbits. Is this clear now? How these masses are going? This mass and this mass will go like this. Will go like this. Okay, I hope this is absolutely clear. Can we find those distances? Definitely we can. It is not at all difficult. I'll tell you how. If this is R1, if this is R2, this is R2, this is basically your R1. We know R1 plus R2 is the total distance which is R, and we also know R1 by R2, R1 by R2 will be this mass by this mass. The distances are inversely related to the masses. Small distance because the mass is big, large distance because the mass is small. So R1 by R2, this distance will be for this mass, R2 will be for the larger mass because this distance is more, so this mass, because mass is inversely proportional to the distance from the center of mass. Perfect. So mm cancels. So from this we get R1 into 2 is equal to R2. R1 into 2 is equal to R2. 2 goes over here. So substitute this over here and see what do you get. You will get basically R1 plus 2R1 is equal to R. Therefore, from this we'll get 3R1 is equal to R. Therefore, R1 is equal to R by 3. Once R1 is equal to R by 3, we have got it. Therefore, R2 will be 2 times of R1. R1 is R by 3. So, R2 and R1 we have got. R2 and R1 also we have got. Everyone clear till this point? Everybody clear till this point how we got R1 and R2? Next step. These speeds will also be different. Obviously, both can't go with the same speed. Their speeds will be different. Agree or disagree? Because how can both of them be going in circular path with the same speed? Or I'm talking about V, not omega. Omega will be same. V will be different. V will be different. Now, how do I know whose V is more, whose V is less? Think about it like this. Angular speeds are same because since time period is same. Why time period is same? Because if this completes a circle, this m has to be always diametrically be opposite. So it will take the same time to complete one circle. So time is same, so omega is same. So omega is v by r, velocity of mass m by the distance which is r2 is equal to velocity of mass 2m by distance r1. Omega is v by r. If I write this Vm by R2, what is R2? 2R by 3, and this is nothing but R by 3. What do I get, guys? What do I get? R by 3 cancels. So 2 goes on the top. So velocity of mass m is 2 times velocity of mass 2m. Velocity of mass m is 2 times the velocity of mass 2m. So if this is v, this will be 2 times of v. Hence, I can just put this as v. So this will be 2 times of v. Is this absolutely clear? It kind of makes sense. M to m, v to v. Inversely related. When the masses are 1:3, then speeds will be 3:1. V and 3v. If one is m, another is 5m, then 5m will have speed v, m will have speed of 5v. Always inversely related. Always inversely related. Is this clear? Yes. I will also drink some water. Okay. If this much is understood, let's go and solve the problem now. With practice, you will start writing it directly. You will write it as r by 3 and this will be 2r by 3. Okay. So these are the distances. The force was the only part which was remaining now. Force like this. Force like this. Okay. So if you look at m, so for let's say mass number m, that force is going to act like the centripetal force. Centripetal force for that circular motion will be mass into centripetal acceleration. That force we already know is by Newton's law of gravity gm2m gm2m divided by the total distance, which is r square. Mass considered is m. Centripetal acceleration, remember, is velocity squared divided by the radius. What is the velocity of mass m? It is actually 2v. So 2v squared divided by the radius. Radius of the circle is 2r by 3. Radius of the circle is 2r by 3. Okay. You can see few of the things will at least get cancelled, like this r over here and this r over here. Okay. Maybe this 2 will cancel with one of the two, which is being squared. Another 2 will also get cancelled from here. This 2 and this 2, and another 2 with this 2. Okay. So what is remaining now? Therefore, g m square, nothing is there below. Oh, one of the m also got cancelled. We have to keep that in mind. One of the m also got cancelled. So there is no need of gm square. So g into m is equal to just v square is there. Here 1 by 3 was there. That 3 goes on the top. So v square into 3. That's it. And this r was remaining. That's all. That's all I believe. Yeah, r square, 1 r got cancelled, 1 r is remaining. So therefore, from this I get the velocity is equal to 3 goes below and put it inside the root of gm by 3r. Root of gm by 3r. So therefore, I found v. Obviously 2v also we know. So therefore, velocity of mass m will be 2 times of v. So 2 times of root gm by 3r, and velocity of mass 2m is just v. So that will be just root of gm by 3r. We found this out. We have found this out. Is this clear? Now the question was also on the time period, if I'm not wrong. Question was also to find the time period. Obviously you won't get both the questions together. Either you will get this or that. So time period of rotation, let's say you consider that mass m will be, time is distance by speed. Time is distance by speed. Here the distance is 2 pi multiplied by the radius, which is the circumference, divided by the speed of that mass m. Distance, which is 2 pi r, divided by the speed of mass 2m. Okay. What is that radius? Radius is 2r by 3. So put 2r by 3 on the top. What is the speed? Speed is there right over here for mass m, which is given to be 2 times root of gm by 3r. Okay, 2 cancels. 2 cancels. 2 pi is still there. 2 pi is still there. 2 has cancelled. R is there. 3 is there below. This goes on the top as 3r divided by gm. Perfect. If you want, you can cancel this root 3 and root 3, and you will get this as 2 pi and then r and then root and then r and then 3 times of gm. That's it. That is the answer. Root 3 cancel. Root 3 will remain in the denominator. Take it inside root 3 gm. 2 pi r and r is there inside the root. So that is the answer for our time period of revolution. Is this absolutely clear, my dear students, how we solve this question? So this is a good level question of dual mass system trying to revolve around each other, which involves the concepts of circular motion as well as center of mass. So what have we done in this particular question? We first identified that it is actually revolving around the center of mass. It is at rest. They both have different orbits, different radius, even different speeds, but same angular speed because it has to take the same time period. The mutual force is just given by Newton's law of gravity. Second thing, we figured out what is the radius, what is the speed ratio, everything, v, 2v, r, 2r, whatever it was. And then finally we applied concept of circular motion for this mass. You might ask, sir, what will happen if I applied for this mass? Will you get the same answer? Answer is obviously yes. It's just that I have chosen m. If you try the problem, At home for 2m, you will exactly get the same answer. There will be no difference at all. Clear? Oh? Beautiful question. Awesomeness. Let's move. So we have done this also. We have done this also. Okay, perfect. Right. Next question, guys, coming up on your screen. Okay, try to solve this particular question as well. Question is, find net force on 3m. Question is, find the net force on the 3m mass. Other masses are placed as shown. I want everybody to put in sincere effort in your rough books, rough sheets, newspapers, whatever you are using, and try out this question. Okay, try out this question. We'll be obviously doing it together. 3m will get pulled by 4 masses in 4 different ways, 4 different directions. 1 by mass m, 2m, 2m, m. Distances are also slightly different. Be careful about it. So the resultant will be in some weird direction maybe. You need to be very careful about the directions as well in this particular problem. Alright, so try it out. If you do it systematically, you will get the answer. If you think of this particular force, this will be F1. This particular force, let's say F2. This particular force, let's say F3. And this particular force, let's say F4. These are the 4 forces. I think first we'll find the x component of force, then the y component of the force separately, and then we'll try to solve the problem. If you look at the x direction, this distance is more, the mass is more, distance will have more effect because inverse square of the distance. So I think F1 will be more than F3. If I'm wrong, I'll get the answer negative, no issues. So if I look at the x component of the force, it will be F1 minus F3. Okay. F1 minus F3. F1 is here, F3 is here. F2, F4 are perpendicular, y-axis. What is F1? It will be G m1, m2. So m into 3m divided by distance, which is a square, minus. Similarly, what is F3? F3 will be G 2m, 3m. Distance is basically 2a. So 2a whole square. So you can see G m square by a square is common. What is remaining over here is 3 minus 2 and 2 cancels. You have 3 over here divided by one of the 2 remains over here. Just check this out. 2 cancels, 3 is there. One of the 2 remains over here. So this will basically become 3 minus 3 by 2. We can take 3 outside common. 1 minus half is half. So it will just be 3 by 2. So 3 by 2 G m square by a square is the x component of the force. Leave it. And now let's go to the y component. Let's go to the y component also now. So what will be the y component of the force? This minus this. F2 and F4, they both are opposite, so they should cancel out partially. F2 minus F4, right? That is what it should be. What is F2? F2 is G2m into 3m product of the masses divided by the distance square minus F4 Gm into 3m whole thing divided by distance, which is basically 2a and then whole square. Okay, so as you can see, Gm square by a square is common. Here you have basically the number 6. 2 into 3 is 6. 3 is there, 4 is there below. So 3 by 4 over here. 6 minus 3 by 4. I hope this is absolutely clear. So therefore 6 minus 3 by 4. 4 6 are 24. 24 minus 3 is 21. So 21 by 4 and you have Gm square by a square. So if the net force was asked, the answer will be, since the answer is positive, that means whatever direction I have assumed positive is correct. So it will be Gm square by a square. X component is 3 by 2. So 3 by 2 I cap. 3 by 2 I cap. Y component has 21 by 4. So 21 by 4 J cap. So that is the force which is acting in some weird direction. If the magnitude is asked, you will obviously take the mod value. That is very simple. But you understood how to solve this question, I hope. Is this clear? Are you now confident about the force of gravity related questions? Gravitational force, 2 masses, 3 masses, 4 masses, masses moving around each other, breaking of masses, common question, guys. Common question. Very good. Next, let's talk about energy, gravitational potential energy. Now, let's talk about gravitational potential energy. Remember, gravity is a conservative force. The force of gravity is conservative in nature. Do you remember conservative forces? What is the meaning of it? No matter how you go, the work done only depends on the final and the initial point. How you go does not matter. Path does not matter. It is like a state function. Number 2, if you go and come back to the same point, total work done by the force is 0. Gravity, elastic, spring, electromagnetic forces are conservative forces. Evil forces like your viscous force, frictional force, air resistance, normal, tension, they are not conservative in nature. Only conservative forces have something called as potential energy. So obviously, when two masses are separated, so when masses are separated due to their configuration and mutual gravity, they have stored energy. They have stored energy form. With ability to do work. With an ability to do work. It has ability to do work. Therefore, it has the gravitational potential energy, that is UG. G stands for gravity, U stands for potential energy. So any masses which are placed close to each other, separated by some distance, because of gravitational force, they will start getting attracted, they'll start moving, they are doing work. So where does this work come from? That means they had something stored. Imagine you slept well, you have eaten nice food, so you have stored energy. So next morning you will go for running, you might do some work, but you are tired, even though you slept, and you are exhausted, you have no mood, you are sick, then you will not do work. That means you don't have energy stored inside the body. So whenever these masses get pulled, they start moving, they are moving. Where did that motional energy, how are they able to push things, how are they able to move, how are they able to work? That means they had stored energy. So that energy which was stored was only because of gravitational force. If gravitational force was not there, they will not attract each other. So that is why the name given to them is the gravitational potential energy. Is this absolutely clear? Everyone with me? Okay. Absolutely clear? Perfect. Now you need to know certain things. You need to know certain things. Number one. When two masses are separated by an infinite amount, that means really very far away, then such a situation, please keep that in mind, very important, such a situation where the masses are really far away is then defined as our zero configuration situation. That means energy of those two masses for infinite separation is assumed to be zero. This is your zero reference. This is your zero reference. So when the masses can't see each other, one mass is in this solar system, other mass is not even in the next solar system, towards the end of the universe, that mass doesn't even know, can't even see, it's so far away, then we assume the energy of two masses to be zero, really far away. Now, when the masses come closer and closer, tell me one thing, will these masses find each other and become happy because of their mutual gravity, or will they become sad? Imagine Pandu, Champa really far away. Pandu's mom and dad told you cannot meet Champa. Champa's mom and dad told you cannot meet Pandu. They don't even know that each other exist. Someday they are crossing each other. Pandu sees Champa. Champa sees very far away Pandu. They start moving towards each other. Will they become happy? They attract each other. Oh, they will become happy. They will start coming close. They become even more happy. So once things start becoming happier, their potential energy starts becoming less. Potential energy, something has more potential means it is sad. Understand that. When you take a spring and stretch it, it is crying in pain. Why are you stretching me? Somebody pulls your hands. Elastic potential energy is stored. You get sad. Once you are relieved of that stress, relieved of that potential energy, you become happy. So these masses coming close to each other become happy and happier. So their potential energy becomes lower and lower as they come close. I hope this is clear. So as they approach, that means they become happy, their potential energy decreases. So earlier if it was 10, it will become 9. If it was 9, it will become 7. If it was 7, it will become 6. If it was 6, it will become 2. Correct? Getting my point? So it will become less and less. But when they were really far, their energy was 0. What is that energy which is lesser than 0? What is that energy that is lesser than 0, my dear warriors? What is the number which is less than 0? Negative. It will become closer, even more negative. They come closer, even more negative. So that's why the gravitational potential energy for any two masses will always be negative when they are not infinitely separated. Is this understood? So as they come closer, they become happy, their energy becomes lower. So when they are very far away, the energy was 0. So they come closer, their energy becomes lesser than 0. What is lesser than 0 numbers called in mathematics? Negative numbers. Hence their energy is negative. Therefore, the potential energy of gravity is negative for finite separations, for finite distances. Finite means you can measure 1000 meters, 2 meters, 10,000 kilometers. These are finite values. This is infinite value. For infinite values, it is 0. For finite distances which are measurable, they are basically negative. Okay, I hope this is clear. So, when the masses basically now come at some distance, let's say r, which is a finite distance, this is mass 1, This is mass 2. The gravitational potential energy formula is given by negative G m1 m2 divided by R. That's the formula, guys. G m1 m2 by R, but with a negative sign because it will be negative. I just mentioned it. Clear, everyone, till this point? Zero reference at infinity. Pandu Champa can't see each other. That's it. Infinite separation, zero. Anything closer, negative, 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 negative. More closer, more negative. More closer, more negative, more happy. Lesser the energy, more happier they are. It's a stored form of energy, and it's because of the gravitational force, which itself is conservative in nature. Next important point, which you should know. If you have a collection of masses, m1, m2, m3, m4, like that, then all combinations you should try. So m1 with m2, m1 with m3, m4, like that, all permutation combinations you are going to try, my dear students. All the possibilities. Anything left? I don't know. Maybe even this one. So for a system of masses, the total gravitational potential energy is the sum of potential energies of each pair. Every pair will have a gravitational potential energy, so you are going to just sum it off. So U of the system is nothing but sum of the potential energies of each pair of masses. This is again by superpositioning. Very, very important. You will take every single pair and you will add their potential energies. Tell me one thing, if there are three masses, 1, 2, 3, how many pairs will be formed? Quickly put it up in the chat box. I want to read your answers. If there are three masses, how many pairs of systems will you get? 1 and 2 will have some potential energy. 1 and 3 will have, 2 and 3 will have. How many pairs you got? 3 pairs you got. Okay. What if there were 4 masses? What if there are 4 masses? 1 with 2, 1 with 3, 1 with 4, 2 with 3, 3 with 4, 2 with 4. I think there were 6 pairs which were formed. So more masses will not mean that you will have that many pairs. You will have little bit more number of pairs. It's like taking n points and joining it with line segments. There will be nc2, that is permutation combination. It's okay, even if you don't know about it. Basically n into n minus 1 by 2 number of pairs will be formed always. Yeah. Okay. So if you have 5, 1, 2, 3, 4, 5, this with this, this with this, this with this, this with this, then this with this. So how many such pairs can you form? Try to find all those pairs. So usually the total, this is just an extra note, usually the number of pairs which will be formed will be n into n minus 1 divided by 2. If there are 3 number of masses, 3 into 3 minus 1, which is 2, 2 cancels, 3 pairs. If there are 4 masses, 4 into 4 minus 1, which is 3, 4 3s are 12, 12 by 2 is 6, so 6 pairs will be formed, like that. Okay, that's how it is. Number of pairs. We'll do a question on this, so don't worry. All right. Few more things which you should know about gravitational potential energy. Gravitational potential energy, work and conservative force. Few more things which you should know. This we have already done in the chapter of work per energy, but still it is my duty and responsibility to show this to you. The gravitational force will be, remember this, negative du by dr. Force is negative gradient. Force is negative gradient of potential energy. The gravitational force is basically the negative gradient of potential energy. We have seen this in work per energy chapter. F is minus du by dx minus du by dy. We have seen this already, just showing this to you again. Another important thing, the work done by conservative force, work done by external force, and the change in the gravitational energy. The work done by conservative force means the work done by gravity in this case. All of them are related to each other with an equal to symbol, but there is a negative sign somewhere. That negative sign is right over here, the work done by gravity. So minus work done by gravity is work done by external forces, which is also the change in the gravitational potential energy. This is also a very important formula. We have seen this even in electrostatics. Delta U means change in the gravitational potential energy. So the change in the gravitational potential energy is the work by external forces, which is negative of the work by the gravitational force. Negative of the work done by the gravitational force. So very, very important. Okay, so remember these things. So let's go through all the slides once more. Gravitational energy, which is a stored form of energy because of the gravitational force, is negative g m1 m2 by r, not r square. For very far away distance, the standard assumed is as 0. When there are more masses, you take each pair, add their potential energies to get the total potential energy. Usually you get many number of terms in that. And the same principles which we learnt in the work per energy chapter. Du by dr with negative sign is the force. Number 2, external work is change in potential energy, which is also negative of the work done by the gravity, elastic, spring, electric force, whatever, conservative force. That is also still valid. Is that okay, everyone, with me? Let's do some questions now. Say for example, we have a system of masses like this. There is m, 2m and 3m, and the separation is basically A. Question is, find the potential energy of that particular system. Next problem will be, if the side is doubled, find the external work done, delta U, and the work done by gravity. All these three things. Okay, so let's start with the first one over here. Finding the potential energy of the system. You have to find the potential energy of the system. Let's see, how do we do this? Because there are 3 masses, so obviously there will be multiple terms over here. So let's start with that. The potential energy of that system will be the sum of the potential energy of each of the pairs which you can form. There is one pair over here, so minus g m 2m divided by distance, which is A. Next pair, 2m and 3m, negative g 2m 3m divided by A, of course. Next pair is formed over here, minus g m 3m divided by A. Perfect. Did we get this? Everybody with me? Okay. Now can you see negative sign is common? G is common. M and M, which is m square, is common. Even A is also common. What is left? 2 is left. 2 3s are 6 is left. Plus actually. and plus, because minus sign was taken common, 6 3 is 18 is also left over here. So this will be 2 plus 18, 20, 20 plus 6, 26. So minus 26 gm square by A is basically the potential energy of that system. Done and dusted. Minus 26 gm square by A. Everybody got this? Very simple. We have used this concept over here. Potential energy of a system is sum of the pairs potential energy. All the possible pairs you will take. This with this, this with this, this with this. Oh, sorry guys, this was not 6 into 3. I'm so sorry, that was a silly mistake. My bad, that was G. I'm so sorry. So G looks like 6. So chances of silly mistakes in the actual exam. That was just 3 guys, I'm so sorry. That was just 3. Yeah. 1 into 2, 2 into 3, 3 into 1. Yeah. So 6 plus 3, 9. 9 plus 2 is 11. So this will be minus 11 gm square divided by A. Sorry. That's the potential energy of the system. Yeah. Yeah. Correct. That was not 18. That was 3. G looks like 6. Be careful in the actual exam. Okay. This is how silly mistakes happen. Okay. Now let's go to the next part of the question. Next part says the side length is doubled. What will be the change, gravitational work, external work and all of that. So let's try this out. It's not again difficult. See, initially, if you ask me what is the potential energy when the side length was A, it is this. It is minus 11 g m square divided by A. Now what you have done is you have increased the side length. What you have done is you have doubled the side length. You have made it like this. Correct? You have made it 2A. So when you do this, obviously the final potential energy will be the same formula, just that instead of A you will put 2A. Instead of A, you're just going to put 2A. That's it. That's the only difference, right? Oh, so can I now find what is delta U? Obviously, which is final minus initial. Always changes final minus initial. This minus this. So minus 11 g m square by A minus 11 g, sorry, this is 2A, 11 g m square divided by A. So minus minus is plus, so it will become g m square by A minus 11 g m square by A minus 11 by 2 g m square by A. 1 minus half is half, so it will become 11 g m square by 2A. So that is your change in the gravitational potential energy. Change in the gravitational potential energy. Perfect. We got the change. We can find the work, etc. by this formula. We can find the work, etc. by this formula. So clearly, the work done by external force who elongated the sides will be same as delta UG. It will be the same as 11 g m square divided by 2A. So this is the work done by external force. What about the work done by gravity? The work done by gravity is negative of the work done by external force. So it will be negative 11 g m square divided by 2A. That is the work done by gravity. That's all. That's all. As simple as that. Is this clear how we solve this? Everyone, these questions are very, very common. These questions are extremely, extremely common, my dear students. Cool. Let's do one more question coming up on your screen. Let's do one more question coming up on your screen. Here is the question, guys. Try to solve this. It's on a square. Just you have to find the potential energy of the system. Just find the potential energy of the system. This is a square of side length of A. Okay, come on, try this out. There are 4 masses, so 4 pairs will be formed, including the ones here. This with this, and you need to understand that the side length, if this is A, this is obviously perpendicular, right? So this would be root 2 times of A, root 2 times of A, the diagonal length. So be careful about it. Okay. So potential energy of the system will be negative G m with this 2m. Distance between them is A. Then this with this 2m and m minus G 2m with that m. Distance is A minus G this with this m and 2m. Again the distance is A only. Then negative this guy with this guy, G 2m m divided by A. So this and this, 4 sides are completed. Now the diagonals, minus this m with this m, so minus G m m divided by the distance, which is root 2a, this 2m with this 2m, so minus G 2m with that diagonal, so root 2a over here. So this is the potential energy of the system. Lot of things are common. So minus G m square by A is common. Let's see what is there inside. 2 is there, plus 2 is there, plus 2 is there, plus 2 is there here, plus 1 by root 2 is there, plus 2 2s are 4 by root 2 is there. Okay, so many things. So minus G m square by A, 2 plus 2 plus 2, that is basically 8, plus 4 plus 1 is 5, so 5 by root 2. That's it. I think I can leave it like that. So that is the potential energy of the system. If needed, you can take common denominator and all of that. That's okay. But this is the final answer. Minus G m square by A, 8 plus 5 by root 2. This is how our answers will be in the options in the exam. Clear? Shall we go ahead to the next question then? Shall we do the next question, my dear warriors? Okay. Let's see if you can do this. The next question is as follows. So there are two masses which are very far away, and they slowly start coming close towards each other because of mutual gravity, and they increase their speeds, and when they are at a distance of r, they will be approaching each other. Question is, can you find the relative approach speed when they are separated by this r distance? It's a very nice question. Let's try to solve this. Try to visualize two planets, same mass, very far away at rest. Slowly they start coming close to each other, and then they will collide later on, that's okay. But when they are maybe some few thousand kilometers away, maybe that is the distance r, what is their speed with which they relatively approach each other? That is the question, right? Okay. So first of all, do you agree that their center of mass will stay at rest? Their center of mass is going to be at rest. You will be like, sir, why is it going to be at rest? Reason is that force of gravity is an internal force. That force of Gravity is just an internal force, so it can't change the center of mass. So center of mass is at rest, which also means that if this mass acquires a velocity of v, what should be the speed of this mass? Quickly put it up in the chat box. Masses are equal, center of mass is still at rest. So if one of the masses is going with v, other identical mass should approach with which speed? V only, or else the center of mass will begin to move. So both approach with the same speed. If this was m, this was 2m, then this will be v, this will be 2v. If this is m, this is 3m, then inversely related, this will be 3v, this will be v. So masses are equal, speeds are equal. Masses are unequal, speeds are in the inverse ratio of the masses. Okay. Now that we have understood it, that speeds to keep center of mass at rest, speeds are equal for identical masses. For identical masses. Okay. This concept we use, center of mass, silent killer. I have been telling you this again and again. Okay, next, how do I find V? Shall I use F is equal to ma? You will be like, sir, let's use F is ma. But the problem is I can't use that. I'll be like, sir, why you can't use F is ma? Okay, even if you use and find acceleration, you can't use kinematics. Reason is because acceleration will keep changing. Force is different now. More. Acceleration is different. So acceleration is not a constant. So we can't use kinematic equation. Rather, let's use energy conservation. So let's basically conserve the energy. Conserve basically the energy. So when they are very, very far away, they will have some kinetic energy. They will have some potential energy. When they are some distance r away, they will have some kinetic energy and they will also have some potential energy. R is when they are close, infinity is when they are really, really far away. This is the equation which I will write. Final and initial are going to be equal. When they are really far, they just started from rest. So this is therefore just going to be 0. They just started. Energy at infinite separation, that I have already told you. What do you do for infinite separation? You take the energy as 0. Perfect. So let's just take that as a big fat 0 again is equal to. When they are coming close, they have kinetic energies. Obviously, don't say it is half mv square minus half mv square. A lot of people do that. And why people do that? Sir, the speeds are opposite. So one is positive, one is negative. My question to them is, you put signs when things are a vector. This is not even a vector, it is a scalar. So energies will just add simply. So just put plus. Don't put minus. That will be stupidity. Next important thing, potential energy will be negative always. So G M divided by basically R. That's what it will be. Yes, perfect. Yeah, no centripetal or anything because it's not revolving. It is just going in a straight line towards each other. They were left from rest. It's not like they were going around each other, right? So they're just coming towards each other. So take this guy on this side. So G M square by R is equal to half plus half is 1. So mv square, cancels. So Gm by R is equal to v square. Therefore, v is equal to root of Gm by R. Immediately you will see the answers in the options and you will mark it. Root Gm by R. But that is wrong. You will get -1. Because the question asked was, what is the relative approach speed? Relative speed was asked. So my dear students, be little bit careful. So the relative speed of approach, relative speed, V and V will make it V plus V, which is basically 2V. So actually it is 2 times of root Gm divided by R, which is the relative speed. So this is the final answer. Lot of people make that silly mistake there. Is this absolutely clear, everyone? Till this point? Okay, very good, very good. Now, let me also tell you one more thing. Just like we studied force and potential energy, there is field and potential also, just like in electrostatics. So, you have a term called as gravitational field. gravitational field, and that gravitational field, because of a system of masses or mass, whatever it is, at any point is defined as, you find the force acting on a test mass, and divided by that mass, what you get is basically the gravitational field. So the field E is given by, remember this, limit will come, force is there, force divided by our test mass, where that mass limit tends to 0. Force acting per unit mass is given as the field. This is a vector quantity. Yes, it is definitely a vector quantity. Not just that, we can also see the unit will be not volts per meter and all of that, that is electric field. This is Newton and this is kg, so it is Newton per kg. So basically, if you have a point mass m and you are at a distance r from it, then at that distance r, the gravitational field is given just like your electric field formula. Instead of k, you will have g. Instead of charge, you will have mass. Instead of r, it will still be r only, so it will be r square, gm by r square. Same formula what you have studied before for electrostatics are valid over here, even in gravitation. Keep that in mind. But main thing, you should know how it has been defined. Gravitational field is force per unit mass, Newton per kg. That is your gravitational field. Is that okay? Same way, you also have the definition of gravitational potential. It is not potential energy, it is just gravitational potential. So again, if you have many masses over here and you want to find what is the potential at this point, same way you define potential as potential V. Same diagram, guys, is equal to you take the potential energy, whatever that potential energy is there, and divide it by the test mass, limit m tends to 0. That's it. This is obviously a scalar quantity because energy is a scalar. This is joules, this is kg. So unit is joules per kg. Unit is basically joules per kg. Potential energy per unit test mass. Very, very important. Just like force and potential energy were related, field and potential are also related by this term. Electric field was negative electric potential change with respect to distance. Gravitational field is negative dV by dr. This is negative gradient of the gravitational potential. So same formulas are again applicable even over here. You can see a lot of similarities. So field is negative gradient of potential. Same thing, field was given by gm by r square. The potential at this point, just recollect electrostatics. It was kq by r. Instead of k, you will have g. Instead of charge, you will have mass. And distance is as it is, but potentials are always negative. Keep that in mind. So potential due to this mass will be negative gm by r. Same formulas of electrostatics. Main thing is in energy you will have negative sign. Constant k will be replaced by g. Charges will be replaced by mass. No other difference. Yeah, I hope this is absolutely clear. Okay, till this point everybody understood this. Shall we, yeah, then see what will be the different field force formulas even in gravity? I'm pretty sure now you will be able to guess it very, very easily. Observe this now. Observe this now. If you have a ring-like structure, like the ring of Saturn, and maybe you are on the axis of that ring. Maybe you are on the axis of the ring at some distance. This is x. This is the radius. This is the mass of the ring. Then if you ask me, sir, at this point, what is the gravitational field? Just recollect the electric field formula. Whatever formula was there in electrostatics, same formula, just some small changes. K was there. Instead of that, you put G. Mass will be replacing charge, so M will be there. Next, you had X over here. Yes, try to recollect. You will have X over here on the top for the field, and the whole thing will be divided by, recollect, there will be r square plus x square raised to 3 by 2. Yes, you will have r square plus x square raised to 3 by 2. This is the formula. For electrostatics, in gravity, G will come, charge will be replacing by mass. Same thing. Yes, same thing. No difference at all. Can you now think the formula for potential? Just think about it. There will be G over here. Yes, negative sign will come. Mass will be also there. And below you will have this raised to half. You will just have r square plus your x square raised to half. Negative G m by r square plus x square raised to half. That's the formula. If you know electrostatics, doing gravity is a very easy thing. It's a very, very easy thing. Is that right? Next important thing, next important formula which you should know is for a shell. Or hollow sphere. The next thing will be for a solid sphere. So let's do that. First, let's do it for a shell. This is R, mass is M, R. Now there will be two criterias over here. Once you are outside, once you are inside. So this is when you are, let's say, outside. And then the second criteria will be when you are inside. Okay, so when you are outside, the gravitational field, so this is basically when you are outside. Outside the shell means R will be more than the radius of the sphere. This gravitational field formula will be given by, instead of K you will have G, instead of charge you will have mass. It will behave like a point mass as if it is placed over here. So Gm by your R square, that's it. This is the gravitational field when you are basically outside. It will behave like a point mass concentrated at the center. Same thing even for gravitational potential, guys. Gravitational potential will be negative G and then M, whole thing divided by your R. That's it. Again, when you are outside. It will behave like a point mass separated by distance of R. No, any crazy things. When you are inside, there is a small change. We have seen this. That is, R is less than the radius of the sphere. Then no matter where you are inside, the gravitational field is always going to be a big fat 0 inside. And similarly, for the gravitational potential, come on, think about it. It will be constant. It will be negative Gm divided by the radius of the shell. By the radius of the shell. R is a constant. It is not a variable. Small r is a variable. So it is constant everywhere. Very, very important. It is a constant inside. It is a constant which is there inside. Is this clear, everyone? Recollect electrostatics formula. Similarly, for solid sphere, it again behaves like a point mass when you are outside. So the electric field is just given by Gm divided by R square. This is when you are outside. And here you will have R, and the potential will be given by negative Gm divided by R. Negative Gm divided by R. So this is when you are outside. Outside. R is more than R, the radius. But for inside, there is a small catch. For inside, you need to be little bit careful for solid sphere. Let's see what the formulas are. First, let's talk about gravitational field. It is given by negative, sorry, not negative. It is just given by Gm divided by the radius of the sphere's cube multiplied by the distance from the center. It is actually linearly proportional. Inside, it is directly proportional, linearly proportional to the distance from the center. So small r will come. It is not 0 like a shell. For a shell, it is 0, but for solid sphere, it is proportional to the r value. Keep this in mind. Similarly, the potential which is there inside, is given by negative. Instead of K, you have G. Instead of charge, you have mass. The whole thing divided by, be careful now. Then there are some numbers. There is this number 2 over here. And then you have R what is that? Yes, you will have R cube over here. And on the top, you will have 3. 2 cube, 3 squared will be there, minus something. So you have 3 times of r square minus your small r square. This is what the number is. Yeah. 2, 3, 3, 2. 2 power 3, 3 power 2. That's how you can remember this, okay, formula. Otherwise, it will look confusing. So this is the gravitational potential which is there inside that solid sphere. Inside that solid sphere. Okay, done, dusted. So these were the similar parts which were there in electrostatics. You don't have sheet and line and all that. Only ring, shell and solid sphere. You have to remember this. And this is what is similar from electrostatics. We'll do the rest of the things after a small break. Let's take a small break and return. Okay, let's take a small break and we'll return. Okay. And if you have not yet registered for MVSAT, please do that right away, right now. Yeah, please do that. Yeah, MVSAT link is there in the description. Because the MVSAT is online and some centers offline test is there on 27th of October. So make sure you are registering for it, okay? Because don't miss that scholarship test. A lot of free things and materials given to you. We'll meet in some time. I hope I'm audible and visible to all of you. Just let me know quickly in the chat box. Yes, the break time is over. And what a colorful set of diagrams, obviously. A lot of colors out there. Especially the last 3 slides, but it's for your understanding. After this, I don't think you will face any issues. Get back all the kids and make sure you are smashing the like button. If you are not doing that, Shreyas Sir will be like, okay, students not interested, I will not come. So quickly do that right away, right now. Yes, everyone. Done. Everybody is back. Shall we start with the class? Let's start with escape velocity, then we'll go to satellites and then Kepler's laws. These are the only 3 things remaining. Let's do this. Let's start with the concept of escape velocity since we are already on to the concept of energy. We've already seen what gravitational potential energy does and what it is and how you can calculate the system's energy and how the work done by the external force can change the potential energy. So let's start by understanding this concept of escape speed. Imagine you have a planet like this whose mass is m and let's say the radius is basically r. You have a teeny mini rocket, spaceship, whatever over here of mass small m, and you are throwing it with some speed called as v. Imagine the end of the universe. I know it's wrong to show it like this over here, but just for imaginary purposes, somewhere where you're really far away, where nothing else matters. You cannot experience any forces by other planets, other stars, nothing. You are really far away. It's somewhere over here. You throw this satellite, this rocket, this spaceship from the Earth's surface or that planet's surface with v. Slowly the speed will start to reduce as you go forward. The speed will become even less, and let's say when you reach really far away, it becomes negligible. It becomes negligible or close enough to 0. So when it becomes 0, by the way, why is it decreasing? Because of the gravitational pull of this planet. The planet is pulling it, it is decelerating it, so the speed reduces. If the speed reduces to 0 before it reaches infinity, that's it. The gravitational pull of this planet will pull it back and it will fall onto that planet. If the speed is not much, it will go till here, it will fall back. Speed is little bit more, it will stop here and fall here. But if the speed is so much that it reaches infinity, even if it stops, it will never fall back because you have escaped the gravitational field force of that planet because you have crossed infinity. Basically, it never stops. The notes will be uploaded after the session is over. Obviously, it can't be uploaded before, so just after some time. And we'll also upload it in the sheet. We have maintained a proper sheet with all the lectures, the PDFs, the previous years, whatever things are there in a detailed manner. So check out that sheet for all the subjects. That sheet is there. Okay. So check that out. Even the previous lectures. So if the speed is such that it stops, basically it never stops and rather it becomes close to 0 when you are very far away. Such a speed is called as a escape speed of that particular planet. This escape speed, which is your escape speed, it is number one, you will see it is independent of the angle of projection. Yes, it is independent of the angle of projection. So even if tomorrow somebody throws that mass like this at some angle, let's say like this, then even then you will see that, maybe show it here. Oh, okay, taken. So you will see that probably it will reduce and it will escape into infinity, but it will not be dependent on the angle at which it is being projected. It will go till infinity. You will also see that this particular escape speed is independent you will see that it is independent of the mass being thrown, or projected. It does not depend on that small m. It depends on the mass of the planet, but not on the mass being thrown. Okay, that is what it is. So let's calculate that using energy conservation. Using conservation of mechanical energy, we can say that the potential energy on the surface plus the kinetic energy on the surface will be potential energy when you are infinitely far away and kinetic energy when you are infinitely far away. When you are on the surface of that planet, the planet being a solid sphere, we have just seen before the break, for a solid sphere, when you are just on the surface, the energy behaves as if it's a point mass concentrated at the center. Look at this formula, Gm by R, negative sign. It feels as if the entire mass was at this point and you are separating it by this distance R. So therefore, I can say on the surface, when you are there, it feels as if the entire planet's mass is at the center, and this capital M and small m are separated by the distance R, which is the radius of the planet. So it will be minus Gm small m divided by R. This is only because the planet's mass is at the center. The planet's mass is at the center. Center to the surface, the separation is R. The kinetic energy of the system, only this small mass is being thrown, so it is just half m escape speed square. When you reach infinity, we have seen the potential energy becomes 0 and your speed will be negligible, so kinetic energy is also negligible. Take this guy on the other side, so what you get is half m escape speed square is equal to G capital M small m divided by radius of the planet, which is basically R. Okay, so technically even this over here should have been R, capital R. Small m cancels, 2 goes on the top, so escape speed square will be 2gm divided by capital R. Therefore, our escape speed will be root of 2gm divided by R. That's it. That's the formula. That is the formula, guys. It is not dependent on the angle, nor is it dependent on the mass being thrown. It depends on the mass of the planet. Yes, that is fine. Is this absolutely clear, my dear students? Everybody with me? Perfect. Let's do some questions based out of this. It is given to you. That, oh, by the way, let me also tell you what is the escape speed for Earth and all of that. So the escape speed for Earth is roughly 11.2 kilometers per second, not meters, kilometers per second. So if you throw anything more than 11.2 kilometers per second, it will never ever return back. But this is slightly wrong because we have neglected air resistance, air drag, rotational effects and all of that. So the actual value is much higher than this because the air resistance will suck away some energy. So to compensate that, you have to throw it with slightly more speed. Yes, if you talk about a more dense planet like Jupiter, it is even higher. For Moon, it is slightly less. The escape velocity for a black hole, black hole are so dense objects, masses, that even light can't escape. So for black hole, the escape velocity is more than c, which is basically your speed of light, which is 3 lakh kilometers per second. This was just 11 to 12 kilometers per second. Imagine 3 lakh kilometers per second. If the speed of escape is more than that, even light can't escape it. Nothing can, because nothing can travel for more than the speed of light. So for black holes, the escape speed is more than c, more than or equal to c. I hope this is absolutely clear. Everyone? Yes, hello everyone. Join in. Even if you are joining in late, watch the replay of the missed part later on. All right, so let's take up some questions. This is a spaceship and it is really, really far away. Really, really far away. This is the surface of the earth. This is basically your earth. Question is, when it falls on the surface, with what speed does it fall on the earth's surface? That is the question. There is a spaceship which is very, very far. It slowly gets pulled by the earth and it slowly falls onto the surface of the earth. The question is, with what speed will it fall on the surface of the earth? Very interesting question. There is a very easy logic to solve this. And the logic goes as follows. Imagine this was the earth. This was the spaceship. You throw it with some speed. The speed reduces until it stops over here. And it stops at a very, very far away place. At a very, very far away place. And it never returns back to the earth. Now you do the exact reverse process. It has stopped. It slowly accelerates, increases the speed and falls down. If while throwing outside the planet, the speed with which you throw was VE and it stops here, naturally the exact reverse process, the speed will increase by acceleration and it will have the same speed V. So therefore, the speed of that fall will be the escape speed for Earth, and we know for Earth it is 11.2 approximately. So 11.2 kilometers per second is the correct answer. So it will fall with the exact same speed. You just have reversed the situation. Instead of falling like this, you throw it, it will stop over there. So whatever happens while going far away will happen while coming onto the surface of the planet. As simple as that. Cool. Let's go ahead to the next question. Question is M1 by M2, rather I will put it as R1 by R2 is 1:2. Density 1 by density 2 is 2:1. Find the ratio of the escape velocity of the first planet upon escape velocity of the second planet. The radius of the planets are in the ratio 1:2. Density is in the ratio 2:1. Question is, find the ratio of the escape speeds of the planets. Thank you so much for all the lovely wishes that you guys keep giving. Lovely comments. Means a lot. Thank you so much, guys. And keep loving the sessions, keep liking the sessions, and also help your friends join the sessions. Tell them about the teachers on the channel and how we are teaching you for your exams. It would be a great help, correct? Because you are knowing your friends, your classmates better than I do. All right. How do we do this? Here, the question is on density radius, which is given, and you have to find escape speed. Density, how do I relate? Okay, one thing I know, that mass and density and volume are related, and we know that density is mass by volume. So therefore, mass will be density multiplied by volume of a sphere, which is 4/3 pi r cube. That is the mass. Okay, so what then? Then I'll go back to the escape velocity formula. Escape velocity formula which was there, it was root of 2 times g mass by the radius. So how about this? 2g by radius is there. Instead of mass, you put it as density into 4/3 pi r cube. So what will happen now? Check this. 2 into 4 is basically 8. Pi as it is. 3 as it is. G as it is. All these are constants. Don't do anything with it. Density is there. R cube and R square will be there. It will go outside. So I think I'll be left with R outside the root. R cube and R square. Square root of R square is R. That's it. 4 2s are 8. 3 has come here. Pi is there. D is there. G is there. Perfect. So this is the escape speed formula. From this, what do you get? Escape speed is proportional to R as well as proportional to root of density. Proportional to r as well as root of density. Now my job is straightforward. So therefore, escape velocity 1 by escape velocity 2 will be proportional to radius, right? r1 by r2, proportional to root of density. So d1 by d2. What is radius ratio r1 and r2? I think it is 1 and 2. I think it is 1 and 2. Yes. d1 and d2, that is basically root 2 by 1. Root 2 cancels. I will get 1 by root 2. So escape velocity 1 is to escape velocity 2 is in the ratio of 1 is to root 2. That is the answer. That is the answer. 1 is to root 2. Understood how to solve these questions? These questions are again very, very common. Keep that in mind. Ratio questions on escape velocity. You open any previous year papers, you will find it. 100% it will be there. Then next type of question. If small m is thrown with escape velocity by 2 speed upwards, find the maximum height reached from the surface. Maximum height reached from the surface. Very interesting question. Think about it again. Usually, if you throw anything, with escape speed or more, it will escape the planet's gravity. If you throw it with slightly lesser speed, it will not be able to escape the planet's gravity. So somebody has thrown it with a slightly lower speed, like you can see, escape speed by 2. So what happens is that particular object will probably only reach till some point over here before, stopping, stopping over here, before it stops over here. So this is that height which it has reached. This is that height which it has reached. So the question is, what is that height which it reached before it stops? Is this question clear? Because the speed is lesser than the escape speed. Now you will be like, sir, can't I just use, maximum height formula? 1D projectile, h is equal to v square by 2g. Can I use this or no? Come on, quickly tell me in the chat box. Yeah, the NCERT line by line is done on the NEET English channel for 12th standard syllabus. Yes, 12th standard syllabus. Don't worry, it will be done. Almost, I think, almost the first book is over. Almost 6 chapters are over. And soon, the remaining chapters will also be done. We can't, because g is not constant. I can't use it. So please do not use this. So I'll make a special note also of that. H is equal to velocity square by 2g can't be used. And the reason for that, g is not constant. Because the speed is very, very large. It will go to a very large height. So for large heights, we can't use. For 1-2 kilometers, okay. 5-6 kilometers, okay. Even 20-30 kilometers also okay. Even till 100 it is okay. But beyond 50, 60, 100 kilometers, then it becomes a problem. And I know it is going to be large height because, come on, escape speed by 2. It is still very large. It is like close to 5-6 kilometers per second. It's a huge speed. So large height. So the only option left with us for such problems is conserve energy. Yes. All you have to do is conserve energy. Let's just put equal to over here. So on the surface, there will be some kinetic energy on the surface. There will be also potential energy on the surface. And when you reach on the top, kinetic energy at the top, and there will be potential energy on the top. Let's also keep in mind what will be this speed exactly equal to. It will be root of 2gm divided by r, the whole thing multiplied by half. So strictly speaking, it is root gm divided by 2r. That is that speed. That is the speed into half, right? And escape speed had root 2 on the top. Root 2 and 2 cancelled. Root 2 remains in the bottom denominator. That is the speed with which you have thrown it. Okay. So on the surface, what is the kinetic energy? Half m, this speed square. So root gm by 2r whole square. What is the potential energy? Actually, it is negative. Actually, it is negative. The whole mass is concentrated here, separated by r. So it is negative g capital M small m divided by the radius of the planet. When you reach the top, kinetic energy is 0. Potential energy is not 0. This distance is there. Let's say this total distance is r. So I can just write minus gmm divided by r. That's it. This is what I can write. Okay, let's see what happens over here on the left hand side. A lot of things are going to happen. This root will go away. This root will go away. It will just become g capital M small m. 2 into 2 is 4. Yes, 2 into 2 is basically 4 times of r minus gm m divided by r. 1 by 4 minus 1 is 3 by 4 negative. So minus 3 by 4 g capital M small m divided by r. That is what is there on the left hand side. Whereas on the right hand side, you will just have negative g mm divided by small r. Lot of things will get cancelled like gmm. This negative and this negative also will get cancelled. So I am just left with small r is equal to 4r divided by 3. Small r is equal to 4r divided by 3. But that is not the question. The question is to find h. This h. So guys, what is that final answer? H will be this small r minus the radius, minus this particular radius. Yes, minus this particular radius. So therefore, it will be 4r by 3 minus r. 4 minus 3 is 1. So r by 3. Radius of the earth divided by 3. That is the answer. Yes, the velocity will be 0 at the top, not at the bottom. Okay, so that's why we put kinetic energy as 0. Potential energy will not be 0. It is not far away. It is decent height only. Radius by earth of the earth by 3. So that is the answer. This is how you solve the questions where you have to find the maximum height reached. Okay, so these were some of the questions. Another question which is commonly asked. Find the size of a planet having mass m, radius r, such that it turns into a black hole. Turns into a black hole. This kind of question is also asked many times. How small will you condense it? Imagine you get one very strong person. You are like, okay, can you like press this object? He'll be like, yeah, I can easily do that. Can you press a bottle? Well, bottle is slightly difficult, but imagine you bring a big machine and try to compress this bottle. It will become a very small, dense object, like a compressor. Yeah. We take r from the center in the previous problem because this solid sphere behaves like a point mass at the center. This is what I explained over here also. Where is it? Here. Whenever you take a solid sphere and whenever you are outside, it behaves like a point mass at the center. So that r is always the distance from the center, never from the surface. So when you are outside, the whole sphere behaves like a point mass at the center. That's why we had to do this modification. Is that okay? All right. Now coming back to this point, a problem. So I compress it, the escape speed will change because r is changing. I want to make it so large, the escape speed, that even light won't be able to escape it. So that is when it becomes a black hole. So escape speed should be more than equal to c. Escape speed formula is root of 2gm divided by r is more than equal to c. Squaring both sides, so 2gm by r more than equal to c square. So basically bring c square below. 2gm divided by c square more than equal to r. Therefore, the critical radius, therefore that critical radius is going to be 2gm divided by c square. 2gm, c square is below. If it is equal to this, it becomes a black hole. Anything less than that, 100%. In fact, there is a calculation done for Earth that critical radius for Earth, guess what it is? It is approximately some 1 millimeter or some 9 millimeters or something, or some around 9 to some 10 millimeters. It's so small. Imagine somebody so powerful or a strong alien comes and compresses the Earth and makes it this small, then the Earth will become a black hole. Even light won't be able to escape it. So understand, black holes are not very huge. They are very teeny weeny objects, but the area around them is pulled by such strong gravitational fields that everything feels to be sucked into it. And the black hole keeps on sucking everything, like swallowing everything around them like a hungry giant. A star comes, it will swallow it, it will condense it. Some planet comes, it will swallow it. Some gas comes, it will swallow it. It keeps becoming bigger and bigger. They are like evil demons out there. Okay, that's what it is. I hope this is clear. That's a black hole. So it is said that our Earth is revolving around the sun. Our nice little solar system is there. Now there are many such solar systems in our galaxy. There are many thousands and millions of galaxies in the universe. Our galaxy is called as the Milky Way. The closest galaxy to us is the Andromeda galaxy, which you can sometimes see in the night sky. Sometime in the distant future, the Milky Way galaxy and the Andromeda galaxy are going to collide with each other. Imagine, it will be such a nice firework. It will be greater than Diwali. Imagine, it is not like two suns colliding. There will be thousands of solar systems in Andromeda galaxy, and both these galaxies will collide and there will be a spectacular fireworks in the universe. We will not be alive to see that, but it will be happening very soon, right? It will be crazy. Yeah. And at the center of these galaxies, you have a black hole. Guess what? You might be thinking black holes are very far away. No, but actually there is a black hole right at the center of the Milky Way. So you would have seen some images of some spiraling thing, spiral stars, right? So we are, so this is the center of the galaxy. There are many arms of that galaxy like this. So this is our Milky Way galaxy, and we are somewhere here. We are not even close to the center. We are really, really far away from the center. So that's your Milky Way galaxy, and there are lakhs and lakhs of galaxies like that. And many galaxies together, they form a cluster of galaxies. And like that, between such cluster of galaxies, like that, there are lakhs of such clusters of galaxies. They are also separated by so much distance. Those local clusters also, there is a combination of such cluster of galaxies. So there is a huge depth in the universe. The universe is very, very vast. Yeah. Oh, you can see that right over here on one of the previous year books. I don't know whether you can see. See, you can see the galaxy picture is right over here. This is our galaxy. The center is the black hole. We are somewhere really far away. This is where we are in the solar system, in a teeny place on that Earth, in a teeny place on that is where we are. And imagine lakhs of such galaxies. Isn't it? Yeah, okay. Now that you have understood about your escape velocity, it's time to talk about acceleration due to gravity also now, before we go to the satellite theory. Now, acceleration due to gravity. Acceleration due to gravity on the surface of the earth or on the surface of a planet. That is what we want to calculate, how much it is. We will be making the calculation, but keep that one thing in mind. Whatever we get is theoretical. Practical value is different. Practical value is different because of the following reasons. Number one, the earth is not a perfect sphere. It bulges out at the equator. It slightly bulges at the equator. So because of that, our calculations are slightly wrong because earth is slightly ovalish in nature. So, we have assumed the earth to be a sphere. What diagram I have shown is very ovalish. Actually, it is almost round. There is hardly a difference of some 20 to 30 kilometers, that's it. Looks to 20-30 kilometers is huge, sir. But think about it. Radius of the earth is only 6,400 kilometers. So, if one place the radius is 6,400, other place the radius is maybe 6,420. That much difference is there, but that small difference also creates a small error in the theoretical versus practical value. Second problem which is there is the rotational effects of earth. Rotational effects. We neglect the rotational effects of earth, and because of that there will be centrifugal effects. Centrifugal effects, centrifugal force will create some different notion. Imagine some person in Africa where the equator passes. He is being thrown out into the air because of the rotational effect. Like when you stand on a merry-go-round, which is going round and round, you are thrown out, right? So same way, the person on the equator will experience huge centrifugal effect as compared to the penguins in Antarctica, which are on the axis at zero distance from the rotational axis of the earth. So rotational effects are also going to be there. And the third one is basically the density is not constant. Density and topography is not constant. Very, very important. Somewhere there is ocean, somewhere there are minerals, somewhere there are mountains, somewhere there are some biological remains. So the density is not uniform, but all the formulas of our gravity and electrostatics, they are for uniform spheres, not for non-uniform spheres. Somewhere there are hills, valleys, oceans. So those effects have been definitely neglected. So the actual value that you get is slightly different. Is that okay? Everyone? Okay, awesome. So what is that value that you get? What is that value that you get? Let's have a look at it. Say for example, this is our planet. This is our radius. You are taking some mass close to the surface. Obviously, it will accelerate downwards with a value of g0. It will accelerate downwards with a value of g0. And there will be also a force acting on it like this. So by Newton's laws of motion, I can say that the gravitational force is the mass of the object into acceleration due to gravity. F is equal to ma. But by Newton's law of gravity, this gravitational force is g, mass of the planet, mass of the object, divided by the distance, which is r square. That's it. This is because the entire mass can be assumed to be concentrated at the center. So the mass of the planet is concentrated at the center. So it feels as if capital M which is the mass of the planet, is over here, and the other mass is over here, separated by the radius of the Earth or the planet. So that's why I have put gmm by r square. So with these two things, I immediately get G capital M small m divided by r square is equal to mg naught. mm cancels. So therefore, acceleration due to gravity is capital Gm divided by r square. A very, very important formula, of course. Okay, this is acceleration due to gravity on the surface of the planet. Now, for Earth, the mass of the planet, that is the mass of the Earth, is roughly close to 6 into 10 to the power 24 kg. The radius of Earth is 6,400 kilometers, which you can convert it into meters. The value of acceleration due to gravity that you approximately get using this is around 9.8 or basically pi square meters per second square for Earth. This is for Earth. G is standard, 6.67 10 to the power minus 11. Mass is 6 into 10 to the power 24 kg. Radius is 6,400 kilometers. Gravitational value pi 3.14, square it, approximately 9.8. That is the value that you will get. Is that okay? That is for Earth. For Moon, it is 1/6. For Jupiter, it is 2.425 times. Yes, Jupiter is more dense, even though it is very big. You will see gravity on Jupiter is slightly more, so you will feel heavier on Jupiter. You will feel lighter on Moon. So on Earth, if you jump like this, on Moon, you will jump like that, like this. On Jupiter, you will feel so heavy. If you jump, you will just fall here. You will jump, you will fall here. So that is how things are. You will feel heavier on Jupiter or denser planets, massive planets, but you will feel lighter on small, teeny, mini, less dense planets. Is that okay, everyone? Thank you so much for all the love, guys. Thank you so much. And keep loving the classes by liking it, sharing it, subscribing to the channel in case you haven't done that yet. Yeah, thank you so much. Similarly, let's go on the top. Acceleration, and then we'll also go below. Acceleration due to gravity at some depth, basically. Say for example, this is our planet. This is the radius of that planet of mass m, and we are somewhere inside over here, mass m. Obviously, there will be some acceleration g d towards the center of the planet. This is the center of the planet. You are at some depth. So let's say from here, if you measure this, from here, if you measure this, that is that depth d. But from here, if you measure till the center, that is small r. This small r is the distance from the center. Distance from center. This d is basically the depth from, obviously, the surface. From the surface. Now, if you want to measure what is this GD, again, let's use Newton's law. Again, you will get the answer. It is not that difficult. So again, using Newton's laws of motion and Newton's law of gravity, the gravitational force will be mass into acceleration due to gravity at d. What is this force going to be? Let's go back a little bit. Let's go to solid sphere and let's go inside the solid sphere, because Earth is a solid sphere. Observe carefully. When you are inside, the field, the forces are proportional to r, inversely proportional to the cube of the radius of the planet, gmr or gmx by r cube. That is the catch. So field, force, everything they are proportional to r. So guys, we need to be little bit careful. Here it will be therefore G capital M small m, because this is force not field. Distance from the center is small r upon the cube of the radius of the planet, r cube. This is m into GD. Therefore mm cancels and GD will become Gm by r cube into small r. So this is the formula. This is the formula for acceleration due to gravity at a distance r from the center of the planet. I hope this is absolutely clear. Is that absolutely clear, my dear warriors, till this point? Okay. Thank you guys so much for the fire. All right, looks like you guys are loving the lecture. So now I don't like this formula. I'll tell you why. Because this is r, distance from the center. I don't want that. I want depth d. So here is what I will do. I'll write it as Gm by r square, r by capital R. You'll be like, sir, why did you do it like this? Observe, r cube as r square into r. Gm by r square is nothing but g naught, acceleration due to gravity on the surface. Oh, now I get it, sir. So this is g naught. What is small r? This small r is radius minus depth. So it is radius minus depth divided by r. So therefore, this will become g naught into 1 minus d divided by r. This is a much better looking formula rather than putting g, mass, radius, distance from the center. This value I know, radius of the earth I know. This is a much simpler calculation. So usually you will solve the problems via this formula. Usually. But there is no harm in using this also. It's one and the same thing. They have just been derived from each other. Is this absolutely clear, my dear warriors? Absolutely clear. But remember both of them at depth d. You can see at the center, small r is 0, depth is the radius of the planet, d is r by r is 1, 1 minus 1 is 0, so g will be 0, or if you put r as 0, g will be 0. So gravity at that depth will be 0. At the center of any planet, the acceleration due to gravity is a big fat 0. Is that clear? Everyone? Very good. Next. Acceleration due to gravity at a height h, at some height h. Let's try to see this also. Again, this is our planet. This is the radius. Mass of the planet is m, radius is r, and at a height h. So let's go on the top somewhere. You have taken this particular small mass. This is that height, and this mass will get pulled by the gravitational pull of the earth, and that's why it will accelerate with g h. H stands for height h. Okay. So what is the acceleration due to gravity at height h? Again, using Newton's laws of motion and Newton's law of gravity, the gravitational force is mass into acceleration, which is acceleration at height h. Gravitational force. Earth is a solid sphere, I am outside. The entire solid sphere will behave like a point mass. Entire solid sphere will behave like a point mass. So the force will be G capital M small m divided by small r square is mgh. Therefore, gh will become, will cancel, gm divided by small r square. But what is this small r? Think about it. What is this small r technically? Small r is the total distance. It is r plus h. So it is r plus h whole square. This is the formula. This is the formula, guys. Do you see it is very similar looking to the first formula? Instead of r square, it is r plus h whole square. So it's very, very similar looking. But usually what happens is that when the heights are large, usually when the heights are large, you don't use this formula. Imagine, sorry, not heights are large, my bad, when heights are small. When heights are small, then you don't use this formula. So let's take a special case. If the height is much lesser than r, that is basically you are close to the surface. When you are close to the surface, things are slightly different. What happens is, you take this on the top, you will see one very interesting thing happening. Gm, take r outside, r square, one plus h by r whole raised to 2, which is gm divided by r square. I had taken r square outside, so I have written it like this, into 1 plus h by r whole raised to minus 2. I don't know how many of you realize this is like a binomial theorem or binomial form, where you have 1 plus x whole raised to n approximately is 1 plus nx. H is very small, so this is very small number like 0.005 or something like that. So it will be 1 plus the number into x. That's it, guys. So just go with that binomial approximation and you will see that the gravity at height h will be gm by r square. This is 1 plus n is minus 2 into x, which is h by r. But wait a minute, what is gm by r square? What is gm by r square? It is g naught. Gm by r square is g naught. So that's it. So this will just become g naught into 1 minus 2h divided by r. But this is an approximate formula for small heights only, not otherwise. For small heights. If the heights are 50, 60, 100 kilometers, you can use it, because 100 kilometers is very less for 6,400 kilometers, which is the radius of the earth. But for 500-600 kilometers, don't use this formula. You will obviously use this formula. Is this clear? Next important thing. If you notice, this formula looks very similar to the depth formula. G naught 1 minus d by r. Very similar. The difference is you have 1 minus depth by r, whereas for height you have 2h by r. So that number 2 plays a role. Another difference is this is only approximate for small heights, whereas this formula is not an approximate formula. It is an exact formula for all the depths. It's not like it is only valid for small depths, it's valid for all the depths. If you keep these things in mind, it will become easier. That's why I tell, just remembering formulas is of no use. If you don't know when not to apply, when to apply, and how to remember this formula with respect to this formula. How do you compare the formulas? That's very important. Clear? So keep these things in mind. Let's start solving some questions based on acceleration due to gravity, of course. Draw g versus distance from the center. How will the graph look like for acceleration due to gravity versus the distance from the center? Let's see. This is x-axis, which is distance from the center. This is your acceleration due to gravity. I think there should be one point which should be called as the surface. You are at the surface. That is when the distance from the center is equal to the radius of the planet. So when you are inside, the answer is very, very easy. Let's go behind. When you are inside at some depth, the distance from the center, which is small r, is directly proportional to acceleration due to gravity. So it is a direct straight line. So therefore, when you are inside, undoubtedly, I'll just put one simple straight line till here. Okay. Once you go outside, that is basically at height h, this is the formula. As height increases, you can see this is r square. It is inversely proportional to r square. So as r increases, gravity decreases. As r decreases, gravity increases. So therefore, after this point, you can see it is inversely proportional to r square. So it will be like this. So here it is directly proportional to r. Here it is inversely proportional to r square. So therefore, one thing is very, very also clear, that it is maximum at the surface. So it is maximum at the surface. And that maximum value is your G naught, which is Gm by radius square. That is the answer. Is this absolutely clear, everyone, how the graph looks like? We have gone straight with the formulas, nothing complicated. Okay, let's go to the next question. This question, by the way, was asked, okay, whatever I showed you, right, this graph, you can see previous year books, you will see many times this question has been repeated. Next question, find the acceleration due to gravity, number 1, at a depth r by 2, number 2, at height of radius of the planet by 2. That is the question. Okay, let's try to solve this at depth as well as at some height. Okay, let's understand this. So at depth, that means here, this is basically r by 2. The second time is height, so maybe over here. So this is basically r by 2. So at this point and this point, both you have to find. So let's start with the depth first. It is very simple. So acceleration due to gravity at some depth is g naught 1 minus d by r. What is depth? Depth is r by 2. So r by 2 by r. R cancels, it is just half. 1 minus half is just half. So answer is acceleration due to gravity on the surface by 2. So that is the answer at this point inside the earth. What about the height? Now this r by 2 is descent as compared to radius. So when things are descent, you will not use this formula, which is approximate formula. Be careful. Rather, you will go with the actual formula because the height is decently large. Radius by 2, it is some 3000, some 200 kilometers. So gravity at height h will be Gm divided by r plus h whole square. So Gm divided by r plus h. H is nothing but r by 2. R plus r by 2 whole square, which is Gm divided by 3r by 2 whole square, which will make it Gm by r square. 3 square is basically 9. 2 square is 4, which goes on the top. This value is G naught. So it will be just 4 times of G naught, whole thing divided by 9. That is the acceleration due to gravity at height h. Very simple. Everyone got it? Pakka? Clear? How to solve the questions on gravity at height h, depth d, etc. Fair enough? Okay. Let's do another question, guys, coming up on your screen. Here is the next question. The gravity on a planet, or sorry, the gravity at a height equals to its radius, the gravity at a height equals to its radius, is same as the gravity at a depth of 1/4 the radius of other planet of same size, Question is, find the ratio of the masses of the planets. Find the ratio of the masses of the planets. Looks very tricky because you have to understand it. If you make a silly mistake in understanding, gone. The solution will be wrong. So let's carefully do the problem. The gravity at there are two planets first of all. Let's understand that first. There are two planets. This is one planet maybe, and maybe this is another planet. Their sizes are same. It is clearly given. Size is same, means the radius is the same. Okay, so I can do one thing. I can say this is R. I can also say even this is also R. Okay. Gravity at a height equal to its radius. Okay, so I go up by a distance R, and at this point I find the gravity is equal to the same as the gravity at a depth of 1/4 of another planet. So 1/4 is somewhere over here. So this distance is R by 4, radius by 4. This is what is given in the question. These both points gravity is the same. Okay, let's do it one by one. At this point you are at some height. So the gravity at certain height is given by Gm1 divided by R plus H whole square. So this is for the first planet. So Gm1 divided by R plus H. What is H? It is itself radius. So R plus R. So it will become Gm by 2 square is 4. So 4R square. Gm by 4R square is the gravity at height H. This is done for the first planet. Let's go for the second planet. Gravity at depth D is given by Gm by, if you remember, R cube, this mass is M2, distance from the center. What is the distance from the center? Think about it. If this was your depth, R will be R minus R by 4, which is 3R by 4, which is distance from the center. So that small r will be here. So Gm2 by R cube, and then you have 3R by 4. R will cancel, so you will be getting Gm2 3 times. So 3 Gm2 divided by R and R cancel, so R square is there and 4 is also there. So 4R square. So that is your GD. Is this absolutely clear till this point? Okay, I just found out gravity at depth D using this formula, Gm by R cube into R. If you forgot this formula, no issues, go back a little bit, you will remember it. Gm by R cube into R, distance from the center. You can also use this formula. No issues. Okay, I found this formula to be more convenient. Now what is given in the question? The gravity at that height is the same as the gravity at some depth of some other planet. So basically these both are given to be equal. It is just given. You don't have to think, it is given already. Okay, so let's equate them. What will I get the moment I equate them? Gm1 divided by 4R square is equal to 3Gm3 divided by 4R square. Clearly you can see now what is happening. G, 4, R square is getting cancelled. So mass 1 by mass 2 will be equal to 3:1. That is the answer. That is the answer. Is that clear, everyone? This is M2, guys. Sorry. Yeah. 3:1. So this is how you can solve these kind of questions as well. Clear, my dear students? Everybody with me? Okay. So this is how you solve the questions on acceleration due to gravity at height h or at depth d, or basically on the surface. We have done this also. Now the last part about this is satellites. Sometimes it is deleted, some part is not there. So I'll just do everything. If it is there as per the brochure, good. If it is not there, leave that part, but some part of satellite at least is there. Okay, let's do the satellite part. Now the meaning of a satellite is that if you have any planet, some rock, if you have a planet, some rock might be going around it, some artificial natural body will be going around it. That small teeny mini object is called as a satellite. Now there are two types of satellite. One is naturally occurring, like the moon. There was no alien or no person who launched the moon. Okay, moon was there on the earth, let's launch using a rocket and zoom, it is going. No, it was naturally, whatever natural phenomena only caused it. But we have so many spaceships, space stations, rockets and satellites which are going around the earth. Those are man-made satellites. They are coming with a purpose for maybe communicating, maybe television, maybe radio, maybe telephone, maybe internet, maybe spying, maybe mapping, analyzing, weather forecasting. So many reasons are there for man-made satellites. Correct? So that is what are the two types of satellites. One is your natural. The second one is artificial. Natural, example, moon for our earth. But remember, other planets are there with many moons like Jupiter, Uranus, and even other galaxies and other solar system. Some planets have 2 moons, some planets have 7 moons, 8 moons, 9 moons. It's crazy. Yeah. So understand that. So it will be very interesting to be on such planets because that will have even more crazy effects. A single moon causes high tide, low tide, and it has influence on even the human body and so many other biological things. Imagine having 7-8 moons and with different sizes and coming at different times. Sometimes all of them are together, sometimes none of them are there. The ocean currents, everything in that planet will be way different. Okay. Yeah. Artificial are basically used for communication, right? Mapping, spying, etc. So many different purposes are there. And that's why you have the artificial satellite. So a satellite is basically a tiny mass that revolves around a planet using gravitational force to provide centripetal acceleration. Using gravitational force to provide centripetal acceleration. Because who else will make that satellite go round and round? It's not filled with fuel. It's not like somebody is like boom, accelerating and that the satellite is okay, I'm going like this, okay, I'm going like this. No, it's just thrown and it is just going. That's it. Once thrown, there is no air resistance friction in the space. So it keeps on going round and round. Yeah, I hope this is clear. Yes, the whole earth was in my hand. Using gravitational force to provide the necessary centripetal acceleration. That is the working principle, or you can say, of a satellite. All right. So let's derive the equations. It's not that difficult at all. Let's take the planet over here. This is the radius of the planet having mass m. Let's take a circular orbit. In that you have our satellite like this of mass m. That satellite is going with the speed of v, and this distance is basically h, but if you measure this whole distance, that is r plus h, and on this there is a gravitational force like this. Because it is going in circular orbit, there is centripetal acceleration. As you can see, it is doing uniform circular motion. Uniform circular motion it is doing. So definitely there must be centripetal acceleration. So using Newton's laws of motion, force is mass into acceleration. There is only one force, one acceleration, simple it is, and that force is gravity. And this is Earth or the planet. The whole mass can be assumed to be concentrated here. So capital M is at a distance of small r from the satellite of mass small m. So I can just say it is G capital M small m divided by small r square. Why not capital R or H? Did you get it? Because the whole Earth's mass is concentrated here. So imagine one mass here, another mass here. Total separation is this small r is equal to mass into centripetal acceleration, which is v square divided by radius of the orbit, which is small r. Remember, radius of the orbit is small r. So this r over here is basically radius of the orbit. Radius of orbit. Because this is that orbit, radius is this much. R plus H. Okay, what gets cancelled? R, M, M. Okay, no issues. So G capital M by small r is equal to V square. Small m and r have got cancelled. So V is root G M by r. As you can see over here, the small r is r plus h. So I can just put it as root of G M r plus h also. But usually people like to remember it like this because you know small r is r plus h. You can see escape speed was root 2 gm by r. Speed to go in circular orbit is less than that and it is root gm by r. If you forgot what I just said and about escape speed, let me show you back. Remember, escape speed root 2 gm by r. It is slightly more. Root 2 will make it slightly more. But here, if you notice, the speed is slightly less and it will not escape the planet's gravity. It is root gm by small r. Don't get confused. Because these formulas are looking similar, that's why I'm showing them together. Because when you go into the exam hall, suddenly you're like, was it small r, was it capital R, was it 2 here or was it by 2, was it, not there. All these things happen in the hall. So that's why I'm showing it together so that you know which formula to compare with and not to make any silly mistake. Okay, this is done. What about the time period of revolution? So we can also find the time period of revolution. So the time period of that particular orbit can be easily found. That time is distance, which is 2 pi r divided by that speed. So therefore, the time period will be 2 pi r is there as it is. The speed formula is there right from here, which was root of gm divided by r. So here is what we can do now. I'll write it as 2 pi. Instead of r, why not write it as root r square? One and the same thing. And this will become root r divided by gm. The reason why I wrote small r as r square's root is because now I can bring it inside that root. So I'll bring it inside that house and it will look r square into r, which is r cube divided by gm. So that is your time period. Some people also remember it like this: 2 pi root r plus h whole cube divided by gm. That is also fine. but usually this is much more convenient. 2 pi root r cube by gm. Is that clear, everyone? That's the time period of revolution of that satellite in that orbit. Next thing which you should know is the energies of the satellite. The first being the kinetic energy. The kinetic energy of the satellite is half mv square. So it will be half m. Velocity we just got it here, root gm by r. So root gm by r whole square. So kinetic energy will be half, or rather just put G capital M small m divided by 2r. That's your kinetic energy. Similarly, we can also find the potential energy of the satellite. That is just potential energy of 2 point masses. That is standard, guys, negative gmm. What is the distance between the two masses? Small r. So that's it. That is the gravitational potential energy. What about the mechanical energy? What about the mechanical energy of the satellites? That will be the sum of two energies. That will be the sum of two energies. What are those two energies? Come on, think about it. One is potential, which is negative gmm by r, and the first one is, what was it? Kinetic, which was gmm by 2r. This is half, this is negative 1. So half minus 1 is negative half. So energy will be negative gmm by 2r. That's the formula. And you're supposed to remember this. Negative gmm by 2r is the total energy of a revolving satellite. Total energy of a revolving satellite. Interesting thing to note that the kinetic energy is the same thing but without the negative sign. So kinetic energy is actually negative of the total energy. Not just that, you can also see the potential energy over here, that from this, the potential energy over here is similar, just that you have to multiply this with 2, so 2 cancels. So it will be just 2 times of the total energy. This thing was also there in which other chapter? In chemistry also it was there. Modern physics, atomic structure is there. It is very, very similar. Very, very similar, guys. So remember these things in mind. Okay? You will need this for solving problems. Great. Now, you might be wondering, sir, what happens if by chance somebody does not throw this satellite with that speed which is required to go in that circular orbit? Then what happens? Let's have a look at that also. Actually, leave this. What did I just do? Okay. Wait, I will need a new diagram. This is our planet. If you give it exactly that speed which it is required to go in a circular orbit, it will go like this. This is when you project it with exactly root gm by radius. If you throw it, then it goes in a basically circular orbit. Then it goes basically in the circular orbit. But what if you throw it with slightly lesser speed? Imagine the speed of the satellite it loses some speed. Then what do you think it will do? Then it goes in a elliptical orbit. Yes, it goes in a elliptical orbit. We'll be seeing soon Kepler's laws also. You will see that it will go in an elliptical orbit, something like this. This is how it will go. If you reduce the speed even further, you will see it will go even in a smaller ellipse, maybe like this. The ellipse will become like this maybe. So basically it goes in a elliptical orbit. The ellipse becomes smaller and smaller. And in a special case, what happens is, if the ellipse becomes so small, it will probably even hit the surface of the earth. So, it might become so small that it probably just hits the surface of the earth. It was unable to complete its complete path. It was unable to complete its complete elliptical path. So it will hit the surface of the earth if you reduce the speed too much. Lot of people think if the speed is lesser than that, I have heard this many times. People say, sir, it will go like this, like this, like this and fall down. No, it does not fall down like that. It goes in elliptical orbits. So this is what happens for slightly lower speeds. If it is too less, obviously it will go like this only and fall. And if it is 0, it will fall straight on the surface of the earth. Okay, that is obvious. Now what happens if you increase the speed? What happens if you basically increase the speed? So then in such cases, you will see it will be a larger ellipse. Something like this. It will go in a larger ellipse like this. You can see that it is going outside that circle. And if you increase the speed even further, it will go even in a much larger ellipse like this. So it will again go in elliptical orbits only, but these are larger ellipses. And if you throw it with even higher speed, then it so happens that it never ever returns and it goes in a hyperbolic path. Basically, it has escaped the gravitational field of the planet. It goes in a hyperbolic path. So your entire conic sections of your 11-12 standard mathematics is here. You have ellipse, circle, hyperbola. In fact, you also have a straight line. I'll tell you why. Because if you just drop it like this, it is just going to fall in a straight line path. All these things are there. Isn't it crazy? Yeah, it looks like this. This is how the paths are. This is when the speed is more than the escape velocity. Speed is more than basically your escape velocity. If it is exactly equal, right, then there is a small change. Then it is not a hyperbola. If it is exactly equal, then it is a parabola. So these things are very important for interplanetary missions and all of that. I'll tell you why. What happens is, imagine this is our Earth and maybe this is Mars or something, and you want to go from the Earth to the Mars. Okay, maybe Sun is somewhere over here. Okay, so when somebody will launch the satellite from the Earth, it will go like this into the orbit and it will start going in circular orbits like this maybe. It will go like this and then it will probably enter into a circular orbit over here around the Earth. And then slowly you will see they use propellants and they will basically use thrust boosters and all of that, and then they will make it go in a slightly bigger ellipse, then it will go in a slightly even more bigger ellipse, something like that. So they make it go in bigger ellipses like this, and finally, when the final thrust boost comes, it will have such a large speed that it will escape the gravity of Earth, and it will be projected in such a way that when Mars comes here, exactly the timing should match, and then it enters the gravitational field of the Mars, and now they use reverse thrust boosters to slow it down and then again slow it down, and before going into circular orbit, and then finally it reaches the surface of the Mars slowly. So this is how interplanetary missions occur. It's crazy. You have to time it in such a way, because the Mars would have come maybe from somewhere over here like this. It is going around the sun. The Earth was going like this. You have to also consider the rotational effects of the Earth. It has to be timed in such a way. Okay, so this is how interplanetary missions happen. Understood, guys? Clear? So the theory behind that is exactly this: ellipses, hyperbolas, parabolas, straight lines, circular. So if you thought that maths is not useful, the problem is the teacher does not know where maths is used. That's what I would blame. Okay, it's not that maths is not useful. Maths is useful everywhere. You can't live without maths. If you are a person without maths, something is wrong with you. Okay, now let's come to the different types of satellites also. So the first one being called as a surface satellite. If you are very close to the surface, it is called as a surface satellite. In case of a surface satellite, the height is much lesser than the radius. You can see the height is very close. So in such case, what happens is the speed of the satellite will approximately become gm upon r plus h will be negligible as compared to r. So even if that h is there, you can say it is root of gm by r. That is what the speed will become. In fact, even the time period, if you remember the time period also, we have written down the formula, will now become 2 pi root r plus negligible value. This will be now approximate whole cube by gm, which will approximately be 2 pi root of r cube divided by gm. So that's what the time period will be. Now it so happens that for Earth, if you launch a surface satellite which is very close to the surface, like the International Space Station, example, International Space Station, not ISIS, this is International, ISS, International Space Station, which is a surface satellite close to the surface, because you have to make frequent trips, food has to be sent, okay, somebody has to come back, okay, we have to send an astronaut, okay, we collected a sample. So you need to make frequent trips, so that's why it's very close to the surface. It's typically 400 kilometers from the surface of the Earth, just 400, that's all, not much. Okay, so you will see that the escape speed comes out very close to, I think, around 8 kilometers per second. That's huge, but not very huge. It's less than 11.2, which is the escape speed. And the time approximately comes close to 90 minutes. Yes, 90 minutes. Imagine people in the International Space Station go around the Earth in just 1.5 hours. We take 24 hours. They just go around the Earth in just 1.5 hours. That is what they do. Okay, this is for surface satellite. Everybody clear about this? These are surface satellites. Meaning, if this is the Earth, okay, maybe I can have a spaceship. This is my spaceship. So it is going International Space Station. It will be like this, going like this. It will be going like this, very close to the surface. So you are very far, then it will take more time to reach the space shuttle, right? So it will be going like this around the surface of the Earth. Okay, this is what it is. The next one is a polar satellite. Polar satellite. Polar satellite means, see the earth is spinning like this. This is the axis. Imagine a satellite going like this. It is not going over the poles, North Pole, South Pole. It is going like this or like this. It is some weird satellite. But imagine a satellite going like this. So it is going over the North Pole, then South Pole, North Pole, South Pole, North Pole, South Pole. As the earth spins, what will that satellite do? If that person looks below, he will first see Russia. Okay, Russia is there. Okay, then penguins are there. Oh, Australia is there. Okay, India is there. Okay, Kazakhstan is there. Russia is there. Canada is there. Alaska is there. Okay, Africa is there. Every time he will see different things as the earth spins. As the earth spins, think about it. Visualize this. Earth is spinning as you are going in the polar regions, one pole to next pole. You are spinning over different countries and continents. So you can use it for spying, mapping, everything. You want to spy on other country. So you can use it for that. So that is basically called as polar satellites. They are basically called as polar satellites. So they basically go over the poles in different orbits. All these are basically polar satellites. What are they used for? Examples for spying, for mapping, etc. They are used for that, polar satellites. Even our GPS satellites, some of them are polar satellites as well. Okay, so basically they travel over the north and the south poles containing the axis of the earth, containing the axis of rotation of the earth. That is why it is called as the polar satellite. Remember, the north pole is over here. This is north pole. This is your south pole. Is this absolutely clear, everyone? Yes, perfect. The last type of satellite that you need to know is this one, a very unique satellite. I don't know why it became like this, but anyways, you get the idea. It's going something like this, where this is the axis about which the earth spins, and the satellite is always ensuring it is always in front of it, in the equatorial plane. Imagine the equator. This is in the equatorial plane. Just try to visualize the equatorial plane, which contains the Earth's equator, which basically contains the Earth's what? Equator. So this is the Earth's equator. It is containing the Earth's equator. Just imagine that it is going in that equatorial plane. So such a satellite is called as a geostationary satellite. Geostationary or geosynchronous satellite. So the speciality of that is it feels synced with rotation of the earth and at relative rest from the surface. At a relative rest from the earth's surface. So if you always see in the sky, always it will be there. It will never be like it is going here, then here, then here. Why is this used? If you've seen, when you use your cable TV and all that, there is antenna which is focused somewhere. You can't say, oh, today I want to watch IPL. Where is the satellite? Hey, Chintu, go. Hey, Pandu, go. See where the satellite is. Oh, it is here. Papa, the satellite has moved here. Okay, move the antenna here. Oh, the satellite went there. You can't keep moving the antenna like a fool, right? It has to be focused at a place. So, for such TV reception, for sometimes mobile communication, those antennas have to be pointing in a peculiar direction. So, those are pointing towards the geostationary satellites. Yes. So, the time period is the main criteria for that. The time period exactly has to be 24 hours or else it won't work. It won't work. Using time period, you can find the distance from the center. It comes close to around 36,000 kilometers, if I'm not wrong, close to that. This is approximate. And the speed of the satellite approximately comes close to 3 kilometers per second. That's the speed with which this goes at a distance of 36,000 kilometers. It's crazy if you see. Is that okay? Everyone? Right. So these are the main things regarding satellites which you should be knowing. The different orbits, the energies, the speeds and all of that. Okay. Let's do some basic questions on this. If a satellite has to be taken into a orbit of altitude 3r from r, find external work new upon old, speed and time ratio. Find that external work as well as the new upon the old speed ratio. That is the question. Okay, let's try to understand this question. This is our Earth. First time this was the orbit. Next time the orbit has been made to something else. That's what it is. This is r. The altitude is r initially. That means the height is basically r. Next time the altitude is basically how much? 3r. So this is your 3r. So be careful, the radius will be slightly different. So if you mention or find out what is the initial energy of the satellite, which is negative gmm by 2 into radius of that orbit, which is itself 2r. Whereas if you figure out the final energy of the satellite, which is negative gmm by 2 into radius is r plus 3r, which is basically 4r. Be careful. I hope you got it. Why it is 2r and 4r? Radius of the orbit. So therefore, from this we can find out the work done. The work done externally is the final energy minus the initial energy. So final energy is negative gmm, 2 4s are 8, 8r minus gmm by 2 2s are 4, so 4r. So therefore, the work done externally will be, this will be positive. So gmm by 4r minus gmm by 8r. Gmm by 8r. How much will it be? It will be 1 by 8 only. So gmm by 8r is the work which is done externally. So this is the first part of the problem which is done. Okay. Next part. Next part of the problem. It says that you have to find the ratio of the speeds and all of that and the time period. Okay, let's do that. See, when you talk about speed ratio, speed is root of gm by r. Rather, speed is inversely proportional to root of r. Therefore, speed of the first time versus the second time, or I think new upon old is asked. So new upon old speed is asked. It will be radius of old, radius of new, inversely related. Therefore, the new speed upon the old speed will be, what is the old and the new radius? Old radius and the new radius. Come on, think. Old radius was actually r plus r. R plus r, which is 2r. The new radius, it is r plus 3r. Altitude is 3r, which is 4r. 2 and 4 cancels, becomes 1 by 2. So I think you should get this as root of 1 by 2. R also cancelled, or 1 by root 2. That is the answer. Is this correct? Everyone with me till this point? Absolutely clear? Very good. What about the time period formula? Time period is 2 pi root r cube by gm. Therefore, time is proportional to root of r cube. Therefore, time new by time old is root of new one. The new one is 4r. So 4r whole cube. The old one is just 2r whole cube. Okay. So what will this give me? R cancel, 4 by 2 is 2. So it will become, just become 4 by 2 is basically just 2. So it will just become 2 cube. 2 cube is 2 into 2 square. So it will become 2 root 2 upon 1. So that's the answer for the time periods ratio. Clear, everyone? This is how you can solve these questions based on time, speeds and all of that. And sometimes they will directly ask you a question on geostationary satellite or polar satellite. What are the uses? What is the speciality of it? Or just surface satellite. What is the time? What is the speed? Etc. These kind of questions they ask. Now let's just go to the final part. Kepler's law is usually deleted, but still I'll give it to you. Before going ahead, you should know one thing. There is a diagram called as ellipse. This is a circle. You make it slightly ovalish. It is basically called as an ellipse. This is circle. You make it ovalish. It is called as a ellipse. Like you have parabola. This is ellipse. In that you have to know few things very clearly. Number one, this and this, what are they? Basically, this is called as the minor diameter. Minor diameter. This is big, so that's why it is called as the major diameter. Just like you have in a circle, any point to any point you can join, the length will be the same. It is just called as the diameter of the circle. But here, this is minor diameter, this is major diameter. Also remember, the radius of that circle is the same no matter where you go. Let's say I call it r, but here it is not the same. From here to here, the radius is different. That is, let's say a. From here to here or here to here, it is different. Along the biggest one, this is b. This is biggest radius, b. A is the smallest radius. Okay, I hope you are able to identify the differences. Just like you have at the center. This is the center of the circle. This is also called as the center of the ellipse. This is the center of the ellipse. If you ask me minor diameter and major diameter, what's the value of it? Minor diameter will be a plus a, which is 2a. Major diameter will be b plus b, which is basically 2b. That is something again which you should be aware of. The extra thing which is there in an ellipse is something called as the focus. There are 2 points. This is F1, this is F2. They are called as the foci. Foci is plural, focus is singular. Correct? Like man, men, woman, women, singular, plural. Focus, foci, like that. F1, F2 are called as the foci of the ellipse. The special property of the focus is that if you take any point, no matter where you go, you take any point on the ellipse, join it with the focus, and let's say the distances are R1 and R2, you will see R1 plus R2 will always be a constant. That is what it is. If you take R1, R2 as 2 distances from the point on the ellipse, no matter this plus this, this plus this, this plus this, this plus this is always going to be the same. That is the speciality of ellipse and focus. So these are the basic things that you should know about ellipse. Rest everything is not needed. You don't need too much conic sections and all of that. So let's start with the first law, Kepler's law, the first Kepler's law. Then we'll go to the second Kepler's law, and lastly the third Kepler's law. The first Kepler's law says that every planet or every small mass around a massive mass always goes in an elliptical orbit, or worst case circular orbit. So a small mass moves in an elliptical or basically circular. By the way, let me also tell you, for a circle, both the focus are the same. F1 and F2 coincide at the center. Coincide at the center for a circle. The more you stretch them, F1, F2 are apart, the ellipse becomes more ovalish. If F1, F2 come together, the ellipse becomes a circle. Keep that in mind. So that's why I said a small mass goes in an elliptical or circular orbit around whom? Around capital M at one of its focus. So that capital M will be at the focus. The other focus, nothing is there. Don't get scared, sir. What is there at the second focus? Nothing is there. Keep that in mind. When it is the closest, okay, when it is the closest to the massive object, that point is also called as perigee point. And when it is very, very far away, this point, when it is very, very far away, it is also called as apogee point. Sometimes it is also called as aphelion, perihelion. P for pass, close, closer. Perigee, perihelion, apogee, aphelion. These are all Greek names which are given, just so that you know. This is the first law which you should know. The second law is that if you see the planet, it is sweeping some areas actually. Here, if you join the planet and the sun or the massive object, it has covered some area. This is that area which it has swept in some time. This is that area which it has swept in some time. You will see no matter where you go, it will sweep the same area. So maybe it is here, or even here. It will sweep the same area. Here also you will see it will sweep the same area, guys. Because the distance is far, so the distance covered over here is less to keep the area same. So basically the area swept per unit time is constant, is basically constant. The area swept if it is dA, time taken if it is dt, that constant is L by 2m, where this L is the angular momentum, which is itself conserved. Angular momentum, remember, is always conserved when the torque is not there. So there is no torque actually on that planet. So you will see angular momentum will be conserved. So L by 2m, mass of the planet. So dA by dt is L by 2m. This is something which will remain constant. Which means also that over here, because it has to cover the same area, it moves more. So the speed is more speed over here. It moves fast. Here it is slow. Here it is slow because it will cover less distance to maintain the same area. That is your second law of Kepler. This was the first law. This is your second law. What is the third law? What is the third law? Let me tell you that also. Remember, I had mentioned about this thing over here. This is A, this is A. For that planet, which is revolving like this, the time period of revolution is directly proportional to the cube of the major diameter's half length, which is A, and this is actually squared over here. The square of the time period is proportional to the cube of the diameter's half length, which is basically A. What happens is, in case of a circular motion, it is very, very simple actually. For a circular motion, for circular orbits, you will see that this distance is itself the radius, and even if you put r cube over here, proportional over here, this is t square. We already know this formula, guys. 2 pi root of, for satellite, r cube divided by gm. If you remember this, exactly from this you get this. Square both sides, t square, this is r cube. We have seen this formula for circular motion of a satellite. We have already seen this, isn't it? So guys, this is where the major diameter's half length is the radius. But when it is an ellipse, you always take the major diameter's half length, which is A. That's all. That's the difference. Keep that in mind. So these are the main 3 laws of Kepler which you should know. Just given you the theory. We can solve more problems maybe some day when we are doing PYQs and all of that. Right. So this completes your entire theory, guys. We have done detailed lecture. We have completed the theory part. Most of the questions are also done. Some PYQs are also done. We'll obviously take a special class for problem solving later on. Don't worry about it, for more additional practice. But main thing is, did you learn? Did you enjoy? Did you grasp new things? Were you able to understand this chapter of gravity, which otherwise people leave it as an option? Compulsory 1 question, up to 2 questions can also come from gravity. Keep that in mind. And it is a straightforward chapter when you understand electrostatics, magnetism. There's a lot of similarities are also there. Okay, so do not skip gravity. That's what I would say. And if you have fallen for gravity, just put up in the comments fallen for gravity after the session is over, so that I know that you have reached till the end. Fallen for gravity in the comment section. Yes, do that. And thank you for liking. If you have not done that yet, subscribe to the channel if you have not done that yet. Daily rituals, guys. MVSAT last week, guys. Complete your scholarship admission test, right? Because you will get to know where you stand. Also, all the PDFs, everything are there in a detailed sheet. Check out the link which is there in the description box. Cool. Thank you so much. See you again for the next class. Bye bye. Take care. Captain Shreyas signing off.